Ken is trying to set that up.
Excellent.
Yes, we're recording.
Wonderful. Okay, so welcome to our workshop on how do animal neuromechanical systems perform communication, coordination, and control. And this is a workshop in coordination with the 11th International Conference on Biomimetic and Biohybrid Systems, otherwise known as living machines. And we'd like to thank NSF. All the speakers today are actually involved with the C-Cubed NS NeuroNext network. So as you can see, you're virtually in Cleveland, Ohio, which is roughly halfway between New York and Chicago on the north coast of America on the Great Lake Erie. And just like Paris, it's a city of lights. It's actually it's undergone a tremendous resurgence in the past 20 years. It's actually quite nice. And here is one of our sites where people come from all over to see this, the Rock and Roll Hall of Fame. And you can see in the distance behind that, isn't that the Science Museum? Hello?
Yeah, that's the Great Lakes Science Center.
Right, it's Great Lakes Science Museum. Right, so the shore along there, we have museums and the football stadium. And then, let's not forget Cleveland Clinic. How is it rated this year, Hillel?
I think it's in the top 10 again.
Yeah, it's one of the best in the world, for cardiac care, but they've expanded into just about every other possible health science. And on the left in that picture is actually the health. What is it? What do we call it?
The Lerner Health College. Is that what you're talking about?
Yeah, right.
It's the health education. It's the Health Education Center, which is a joint effort between the Cleveland Clinic and Case Western Reserve University.
So it's got medicine, dental, nursing, everything in it, right?
Yeah.
Giant building. Okay, so, and then here's University Circle, where the Case Western Reserve University actually resides. And this is the cultural center. The Cleveland Clinic is just to the west of us. We're surrounded by hospitals.
So what you can see in the center is the Wade Lagoon, and at the head of it is the Cleveland Museum of Art, and to the right of it is Severance Hall, which is where the Cleveland Orchestra plays. And then beyond the Cleveland Museum of Art are the Botanical Garden and the Museum of Natural History. So it's a lovely place to walk, to picnic and so forth, right in the heart of the city.
And speaking of Severance Hall, there's a beautiful picture of Severance Hall and the interior. You might also know this if you know the movie Air Force One with Harrison Ford. Harrison Ford played one of our best presidents of all time in the movie. Anyway, they used Severance Hall. One night I was here, came by in the evening to do something, and you couldn't go down the street, and it was all lit up and there were helicopters flying around. They were shooting scenes for that movie.
We, my wife and I have had subscriptions to the Cleveland Orchestra for the last, 30 years. And we regularly enjoy reading the reviews in the New York Times whenever they visit Carnegie Hall, where they rate them in the top 5 among all orchestras in the world, which is actually very impressive. It's a wonderful place to hear great music.
And there's a Cleveland Art Museum that Hillel pointed out in the earlier photo. There's a lagoon with a beautiful facade of the museum. And yes, we have a Geary building too. And it's just as crazy as all the other ones. It's really, really interesting. It's hard to figure out whether you're coming or going. And then here's campus. Part of campus is at Delbert, where the president and the provost reside. And this is all the science here. There's physics in here and chemistry in biology, where Hillel is right back here somewhere, right?
Yeah, yeah, a little stone building dating the cornerstone set in 1897, one of the oldest continuous operating biology departments in the country. I just want to make a comment. Case Western Reserve University has its strange name because it's the amalgamation of what were two independent cheek by jowl institutions, the Case Institute of Technology and Western Reserve University. Connecticut had a part of its land was in the West, and that was referred to as the Western Reserve. So Western Reserve University had an excellent medical school and very good humanities. And Case Institute of Technology was a very good technology school. And in 1967, the NSF provided funds to unify the entire university, leading to the rather clunky name Case Western Reserve University, which people think is a military academy, but it's not. It's an amalgamation of those two different universities. And when people have attempted to shorten the name, alumni get very upset. So we either refer to it as Case Western Reserve or as CWRU, and even in the abbreviation is multiple syllables. I'll just make one other comment, which amuses me. Many of you know that Harvard was founded originally as a theological school with its motto being Veritas, and that Yale was a breakaway, and it founded its motto to show that being a breakaway as looks at Veritas, light and truth. And because Case was the Western Reserve of Connecticut, which was dominated by Yale, its motto is looks. The rising sun is our image, and that is based on that. So if you're interested in understanding, being enlightened, that's what Case Western Reserve is about. Hopefully, sometime in the future, we can actually welcome you to campus. It's actually a very, very nice place. One other comment I'm going to make is that when I came to Case in 1987, Science magazine had an interesting article about the effects of climate change and global warming. And they predicted that Cleveland would become the beauty spot of America in about 20 to 30 years because it had its own source of fresh water from Lake Erie. And given the prevailing weather patterns, it would not get either too hot or too cold. I don't know, Roger, what do you think? Are we getting there?
I think we're pretty much there. It's actually quite nice.
It is quite nice.
Okay, so the program is, well, the introduction by Hillel and myself, and Greg Sutton will be speaking first, and then Matt Tresh, and then Matthew Chardon, and Ansgar Bushes, and Gesa Dingus. And Hillel will give a little more detail.
So let's say a few words about what, as Roger and I were putting this together. Instead of asking to creating our own vision and imposing it, what we did was we turned to the members of our network, the NeuroNext network that Roger mentioned at the outset, and we asked them to suggest topics. And very nicely, the topics they suggested, I think, do form a very nice, coherent workshop. One of the things that we're hoping to do is to help you see how you can compare and contrast different neuromechanical systems in animals across different phyla. Our network ranges from insects to slugs to rats and cats, a very wide variety of different species, and understand how in those neuromechanical systems, the different mechanisms allow them to perform functions that are essential for their survival, both for trying to develop more quantitative models, which will help the biologist understand the systems better, and for potentially implementing them in robots, which is the connection to living machines. And in this case, the NeuroNext network is primarily focused on trying to use robots as models, physical models, to understand the neuromechanics. But of course, we have interest in creating novel autonomous devices. So we'll begin with an overview on how the frequency of movement and the size of limbs can affect the control of locomotion. That will be the presentation by Dr. Gregory Sutton. And that provides an overall framework for thinking about how scale affects behavior and control. Then we'll turn to the question of the role of joint stresses and strains on the control of limb locomotion. And that will be the discussion led by Dr. Matthew Tresh. One of the things that's very important in dealing with any kind of complex models in the system is trying to fit the parameters and figuring out how to do that properly, especially in highly nonlinear systems, will be the focus of Dr. Matthew Chardon's talk. and new insights on insect walking, which bridge from single neuron function to the overall system performance of six-legged walking, will be the focus of Dr. Ansgar Bushkas's presentation. And then to further understand how sensory inputs to the insect leg are used for coordination and control, Dr. Geza Dinges will talk about biomechanical and morphological studies of strain sensors, the campaniform cicilla, and explain how their sensing is integrated and can affect control both within and between legs. And we hope that today's workshop will be of broad interest, both to those who are focused more on the biology and the neural and mechanical basis of behavior, and those interested in creating autonomous artificial devices inspired by animals. So those were the general introductory remarks that Roger and I wanted to make. Roger, other things you want to talk about?
I think we're just about ready to start. We got 2 minutes to go till Greg begins the first talk. So you might as well just start introducing Greg.
All right, I'm happy to do that. Greg, are you here? Just out of curiosity.
I noticed, actually, Matt pointed out that it doesn't appear that he's here quite yet. So I sent him an email as a reminder.
Hopefully he'll be showing up. Otherwise, Roger and I will have to sort of on an impromptu basis start giving his presentation. I'm hoping that won't happen.
Ken, could you send him what you sent me?
Yeah.
Yeah.
Did you make sure to send him the link as well as the reminder email?
The invitation is particularly nice.
Okay. I will start talking about Greg, so hopefully that will bring him.
If it makes sense to switch, I could do that.
Okay, well, we will see if he joins us in a minute or so, then that's fine. Otherwise, we will let you go first, Matt, which will be, again, we have to be flexible under these circumstances, I guess. Okay, what would you recommend, Roger? Should we just let Matt go and tell Greg that we'll let him speak as soon as he appears?
Yeah, let's go ahead and start with Matt and I see Badisha's here, and Badisha is Greg's student, so she. And
Steve Rogers is also here, also one of his students.
Right.
So Greg is currently in the United States. He's actually in North Carolina, but he does know about this. So I had an email from him overnight.
Okay, and he's aware that he's on. He was supposed to be on at 9 o'clock this morning.
Yes, I mean it's possible he's got confused with the hours because all the times are expressed in UTC. So it's possible he's not calculated the time. Possibly, I'll send him a quick email, see if I can.
Yeah, that would be a good idea. But I think in the interest of staying on target and on time, we should probably just let Matt go first, and hopefully Greg will show up when he shows up. Roger, do you want to do the introduction for Matt then? Or do you want me?
Okay, sure, certainly. I'll just wing it. So Matt will love this. So I'd like to introduce our first speaker, Professor Matthew Tresh, Northwestern University. Matt works on vertebrate animals, and he's working in the neuronics, in particular in rats and cats. He is at the moment. Sadly, he's also a department chair. So despite that, he's been extraordinarily helpful and valuable in our NSF program. So Matt, please take it away.
Thanks, Roger. And thanks to both of you for putting together the workshop. And it's fun to be part of the Living Machines conference. It's my first time attending, so it's be good to see what everybody's presenting and working on. So yeah, what I'm going to talk about is work we've been doing for the last few years, where we've been trying to, it's looking at the role of internal joint mechanics for neural coordination strategies and the importance of understanding that and really appreciating joint mechanics to understand neural control by biological systems. And I wanted to start out just by acknowledging people who did the work. These are two postdocs in the lab, so Cristiano Alessandro and Felipe Barroso. Both have moved on. Cristiano is now at the University of Milan and Felipe's at University of Madrid as well. And then also to acknowledge the funding for these from NIH and NSF. So the work in our lab, like many people here, is interested in kind of the general question of how does the nervous system choose motor control strategies to produce behavior? And in particular, getting down to the concrete, how does it choose to activate particular sets of muscles in order to produce a behavior? Usually this question's answered or addressed in the context of task behavior, right? So how do you activate a set of muscles? So here's like, 3 EMGs going to 3 muscles in order to produce the kind of aggregate limb mechanics necessary to achieve a task. So if you're talking about, kicking a soccer ball or just kind of going for a step, you want to produce the leg kinematics and the leg torques necessary to achieve that step or to achieve that kick. And so the question here becomes, how do you activate these muscles to achieve these kinds of task performance variables, right? And that's kind of the standard way of thinking about motor control, right? And I think that's true both in biology and also in kind of robotic systems as well, right? How do you get a robot to move from point A to point B to achieve the assembly task? But in order to produce this kind of task behavior, muscles have to act through joints, right? And so if you have, this is just the case of the knee joint where we're kind of focusing on, but in order for the muscles that act, to produce this kind of knee extension torque, they have to act through this kind of weird epiphenomenon, which is a joint, right? So in biology, very few joints look like robotic kind of pin revolute joints or anything. Obviously no pin revolute joints, we have some ball and socket joints, which look more idealized. But, they're kind of these weird creations which exist of bones, plus to all of these kind of connective tissues, the ligaments and the tendons that kind of create this structure, which permits motion in some degrees of freedom and kind of constricts it in other ones. And depending upon how you activate those muscles to produce this kind of knee extension torque, it can create different stresses and strains within the joint, okay? And you can imagine there can be different ways of doing the same task, which can differentially stress and strain these structures, which over time and repetitions of the task might lead to damage and to things like osteoarthritis or joint dislocation, things like this, right? And so the question that we've been asking is kind of, does the nervous system pay attention to those stresses and strains within joints? And how does it kind of integrate those questions, those variables in terms of stresses and strains with the achievement of the overall task of the behavior, right? So what we're asking this question is, does the nervous system activate muscles to both achieve your task? Obviously we do, but then does it also pay attention to these internal stresses and strains when choosing how to achieve that task, okay? So I'm going to talk about a series of experiments which addresses these questions. And this is, important for a few different reasons, right? And so one reason this might be important is in the context of rehabilitation. So in many cases, rehabilitation, if you kind of said, what's your goal for rehabilitating somebody after an injury, is you want them to walk like they did before the injury, right? And that's kind of things of, exoskeleton devices such as the Locomat. The idea here is, can you retrain a person to walk with the same kind of kinematics and the same kind of behavior that they had before they had ACL damage or before they had a stroke, things like this, right? And if the person produces the kinematics that looked like what they did before, then you've achieved appropriate rehabilitation. So the trick with this, though, is potentially, is that after injury, so if you have like an ACL rupture, then the mechanics of your limb have changed, right? And so if you produce the same kinematics that you did before, they might actually cause different stresses and strains within the joints. And you could say, the person's walking perfectly normally, but it might come at the cost of internal stresses and strains, which might lead to osteoarthritis and other things. And that's actually, the incidence rate of osteoarthritis in people with ACL reconstruction is really high. And one of the ideas is that they might be producing aberrant behaviors, trying to restore the thing they did before, leading to these extra stresses and strains. Or on another, if they have a stroke, then maybe your control ability is changed. And so if you try to force somebody to produce that particular kinematics, they might need to do it in a way which activates muscles to reduce aberrant stresses and strains. So the idea is that if you paid attention to these other variables, the pre-injury strategy might not be what you want to do. Maybe you want to do something else, which is a compromise between these, which allows you to achieve the task performance, but minimizes stresses and strains. So what we wanted to do is a series of experiments, that would look at this control of both of these variables, both task variables and joint variables. So the model that we're doing this in is control of the quadriceps muscles in the rat. So these quadriceps muscles are the muscles in the front of your leg. Those of you who've been following Tour de France, these are the ones that the bikers have exceptionally large, kind of sitting off to the side. So in the front of your leg, and they mainly do knee extension torques, okay? So they're out here. And there's, as you might expect from the name, there's 4 of them. So there's 3 vasti, so vastus lateralis, vastus medialis, vastus intermedius. So lateralis is sitting the lateral side of your leg. That's the one that really bulges out when you're a biker. Then you have a medial one. Then you have vastus intermedius, which is sitting deep, kind of, you can't actually see it. It's sitting right flush with the femur. And then you have a 4th one, which is rectus femoris, which is sitting kind of right along the midline of your femur. Okay, and these all kind of funnel in and insert to your kneecap, to the patella, which then funnels through your patellar tendon, which attaches to your tibia. And that's what transmits the forces from these muscles to your tibia to produce a knee extension torque. Okay. So what we're going to do is look at kind of the control of these muscles to try to gain insights in terms of the question of these internal joint variables. So the starting point of this came from, actually, it was a work that we were doing to try to build biomechanical models for the rat hind limb. And what we were doing for that was going in and stimulating individual muscles and then measuring what they did to try to take that information to put it into a model. And what we saw is when we put electrodes to stimulate VM or to stimulate VL, and then we measured the isometric forces and moments at the tibia, right? So we attached a force transducer to the ankle right here at the tibia. And then we stimulated either VL, these are the black arrows, or we stimulated VM in the red arrows. And then we moved the leg to different parts of the workspace. So these are different position of the leg in its workspace. We saw that the forces and the moments for these 2 muscles was basically the same. They're really indistinguishable from one another. So from the point of view of task performance, these muscles are completely redundant. Okay, and essentially what they're doing is both producing a knee extension torque across the knee, extension torque across the knee. Okay. However, if we then did another experiment where we attached a force transducer to the patella, lifted it away from the femur, and then put the patella where it would be sitting, relatively along the femur, and then we measured the forces produced from stimulating either VM or VL. What we saw is, as you might expect, both of the muscles produced a force that pulled towards the hip, approximately directed force, but they had different medial and lateral components, right? So the medial muscle, VM, produced a medial force on the patella, and VL produced a lateral force on the patella. So from the point of view of this internal joint variable, the stresses and strains on the patella, these muscles are antagonistic, right? So we have this case where we have these muscles produce opposing forces at the level of the medial lateral force on the patella, but in terms of the task, they produce redundant actions, right? So this is just kind of summarizing. This is the kind of biomechanics that I like because it doesn't require very detailed models of muscles. It's really relatively qualitative, but it gives us a nice tractable way to set up some experiments to go after these issues, right? So if we want, just kind of summarizing this in terms of task actions, both VM and VL produce this knee extensor torque, right? And then at the level of these internal joint variables, the forces upon the patella, they produce opposing medial and lateral forces, right? Just to complete the picture here, we have the other quadriceps muscles. So we have VI, so that's vastus intermedius. That also produces a pure knee extension torque. Rectus femoris is this other muscle, and it produces a knee extension torque, but it differs that it has a hip flexor torque as well. So its origin is actually on the pelvis, and so it gets you a hip flexor torque in addition. Okay, and then in the context of these internal joint actions, the medial lateral forces on the patella, rectus femoris and VI are along the midline of the femur, and so therefore produce a relatively minor medial lateral force on the patella. So this is give you kind of the biomechanical landscape, if you will, the kind of framework that we're going to use to design experiments to go after this question of whether animals pay attention to both task performance as well as these internal joint variables. So, and basically what we're asking is, does the nervous system activate quadriceps muscles, not only to achieve the task, but to minimize the net medial lateral forces on the patella? So I'm going to show you a few experiments that go after this. So the first one is kind of, in some ways, the most direct. So what we did here is just simply, the idea here is if we add a lateral load to the patella, then if it's true that the nervous system pays attention to this medial lateral load, we should see an adaptation of the balance between VM and VL, their activation, so that there's more relative activation of VM relative to VL, right? So that maybe the activation of VL goes down or the activation of VM goes up. but we should have a shifting of the muscle force to pull you medially. Note that on the context of task performance, adding this lateral load to the patella should really have minimal effect, right? Because this medial force on the patella is not actually transmitted to the environment, right? It's all an internal force just within the bones, within the actual knee joint itself. Okay, so that's what we're going to do in this first experiment. So here's the paradigm. So these were tricky experiments to do. These were done by Philippe, but it can be done. So the idea here is we put in bone screws into the patella. The patella in rats is small, but we can actually get screws into it. And then we put a bone screw on the lateral femur, okay? So we do an initial experiment where we insert those bone screws and put in the EMGs to the muscles to record from their activity. We let the animal recover and then get baseline EMGs. Now the screws are in there, but we get baseline EMGs from that. We then go in and do a brief surgery, just a procedure to attach a rubber band, just a spring. These are like little, what you get when you get braces. We just put that between the screws here. And this is now going to pull with a laterally directed force on the patella, okay? So we attach the spring, and then we measure the ratio between VL and VM over 1 or 2 weeks. And what's nice in this as well is that we can go in and we can cut the spring and look at deadaptation and measure the ratio between these muscles afterwards, okay? And we want to ask is, does this ratio change systematically with the imposition and the removal of this load? So this is just an example. Here's VL and VM activation. This is in a few steps of locomotion. This is when the screws are attached, but no screws are implanted, but there's no spring attached. And you have some activation of these two muscles during the stance phase of locomotion, okay? We then put on the spring. And what you can see is that the activation of VL changes. You can see VL goes down. VM in this animal stays about the same, right? But you can see that the ratio between VL and VM activation changes in such a way that there's less net lateral force on the patella, right? So that if you look at the ratio between these two, VL goes down relative to VM. When we can then cut the spring, what we see is that VL activation goes back up, okay, to where it was before. In this animal, VM seems to go up a little bit as well, but the overall ratio between these two muscles over here is similar to what it was in baseline conditions, okay? So we're seeing changes of the activations of these muscles, these ratios, which reflects the imposition or the reduction or the removal of this lateral force on the patella. And this is just the summary across the animals. So here's the ratio between VL and VM, and we just normalize it to its no spring attached condition. So this is just at 1, that ratio, we find that to be 1 for that baseline condition. We attach the spring and we see the ratio between VL and VM goes down. So there's less net lateral force produced by the muscles on the patella, right? And then when we detach the spring, we see that the force, the ratio goes back to levels that are similar to what were before the actual imposition of putting before, similar to baseline levels, okay? So this is consistent with the regulation of internal joint stresses, right? By putting on the spring, we see that the activation of these two muscles changes systematically to compensate for that medial force, that lateral force that's applied to the patella. Okay, so that's one piece of evidence which suggests that this is that the nervous system cares about these internal joint variables. What's interesting is that this ratio seems this ratio between VL and VM, the change does not happen instantaneously. It seems to take some time to develop, right? So this is looking at this VL-VM ratio. Here again is our baseline condition. If we look 2 hours after we attach the spring, the ratio hasn't changed, okay? But only when we look at 3 to 5 days later do we see this ratio change. So suggesting that it's maybe not a, well, we can talk about the implications, but one possibility is that this might not be, that this ratio, this change in ratio might not be due to an immediate change due to reflex compensation, right? Where the sensory information has changed and now the muscle activations are altered, but maybe more of a long-term adaptation process. So that's one set of experiments. We look at another set of experiments, which is more of an observational study here. And the idea here is then, again, if the nervous system really cared about the net medial lateral load on the patella, then we should be able to see evidence of its active control during normal behaviors, right? And in particular, we should see that the activation between VM and VL should be very tightly correlated, right? So every time we get a larger activation of VM, we should see a compensatory activation of VL to balance out that the net medial lateral load on the patella so that it ends up being close to 0, right? So that we end up with minimizing that net medial lateral load. The correlations of VM to these other muscles, though, does not need to be very large, right? Because RF and DI do not produce much of a medial lateral force on the patella. And so therefore, there's less need for these muscles to be controlled and correlated to one another. Okay. On the other hand, that's in the context of kind of controlling these internal joint variables. If on the other hand, the nervous system really cared about task performance and trying to simplify task performance, okay, then the correlations we see between muscle activations might reflect the fact of muscles activating in a similar way to produce the task behavior. Okay, so given that VM, VL, and VI all produce basically the same net torque across the joint, we might predict that they should be controlled as a unit, or if you will, like something like a muscle synergy, and that the activation should be tightly correlated across these three muscles. Okay, and so we have kind of predictions of what how to interpret the correlation structure in these quadriceps muscles. And if we see one pattern, it would be suggesting that this kind of internal joint variables are important. If we see a different pattern, it would suggest that task performance is more driving these correlations. So we're going to do these experiments during locomotion. So here's just an example of our 4 quadriceps muscles activated during several steps of walking. This is just treadmill locomotion. Here's just showing you iliopsoas to show you the hip flexor muscle and just give you the basic activation profile of these muscles. So all 4 quadriceps muscles are broadly activated during the stance phase. This is the average activation of these muscles, okay? And this bar is the stance phase when the foot's on the contact of the ground, okay? And what you can see is they're activated during stance, okay? But they have different profiles, right? So these both VL and VM show this kind of slow ramping up. The I shows more of a tonic activation and then a down. Rectus femoris is a little bit more phasic towards the end, okay? So we can start to see is just that if you look at kind of the average activation of these muscles across task conditions, this is just showing here, you know, VL and VM seem to have similar profiles, okay? But not similar to VI. If we do this now, we look at different task conditions. So we have animals walking on a treadmill, either level treadmill or going down slope or going up slope, or we change the speed of the treadmill, okay? And this is all during flat walking. And then these traces are showing the average activation of these quadriceps muscles across these task conditions. What you can see is that the red and blue traces, VL and VM, their activation profiles really track each other across task conditions, right? So the activation of all these muscles changes with the task, okay? But the activation of VL and VM change together, okay? And they really kind of seem to track one another. Whereas the activation of VI or RF, they also change across task conditions, okay? But they don't change in the same way as VL and VM do, okay? So this suggests that across these different kind of behavioral manipulations, VL and VM remain tightly correlated. Okay, so that's for their average activation across task conditions. What we also wanted to ask is at a step-by-step level, do the activation of these muscles track one another, right? And so this is just showing you some of the raw data we use. So each dot here is the activation of these muscles, this pair of muscles on one step, right? So this is the activation of VL, was very high on this step here. For the activation of VM, it was more in the middle, right? But then we looked at repetitions of these steps and said, how do these muscles co-vary from one step to the other? You can see here, VL and VM show a fairly tight correlation. You know, it's not perfect by any means, but relatively strong. Whereas the activation, the correlation between these other muscles is not as tight. Okay, there is some correlation, but it's not as tight as the correlation between VM and VL. And so we wanted to ask, was this consistent across our animals and across task conditions? Was the correlation between VL and VM preferentially high? And that's what we saw. So this is looking at the correlation coefficient between VM and VL. That's that first bar, okay? And then here are the correlations between all these other pairs, right? So VM, VI, VL, VI. And what you can see is that VM, VL is very high correlation, about 0.8, okay? Whereas the correlations of these other muscles are lower than one another. And this preferential correlation between VM and VL was consistent across all these task conditions, okay? So, and importantly, the point here to say is that the correlation between VL and VI, or VM and VI, was always lower than the correlation between VM and VL, suggesting that it was really that this correlation, the easiest way to interpret this is in the context of their correlation between the medial lateral forces on the patella, okay? So that's just kind of showing 2 experiments that we did to kind of go for evidence of this that suggests that the animal cares about these internal joint variables, right? So this first one was the perturbation study. We put a load on the patella, show the animal compensates its activation to compensate for that. And then also this observational study to say the correlations between VM and VL were preferentially high. We did another experiment I won't go into here now, but we're looking at, again, a perturbation study where we paralyzed the vastus lateralis and looked at how the animals adapted to this paralysis, this injury, and showed that the adaptation strategies only really made sense if you think about the activation of muscles in the context of their effects on these internal joint variables. If you did not pay attention to the changes, if you did not pay attention to the actions of muscles on patellar load, you would have a hard time understanding why the nervous system chose this particular adaptation strategy. But like I say, I won't go into that. But altogether, these are kind of complementary experiments which suggest and provide support that the nervous system cares about these internal joint variables in controlling muscle activation. Okay, so what we're doing in more recent experiments is asking, okay, we just maybe hopefully, provided evidence to say that the nervous system cares about these variables, and we want to now get to is what is the neural pathway involved in that control, right? So in the first step in that pathway is asking, how does the nervous system know about these? How does it actually accomplish this control? One idea here is that this could be accomplished by joint afferents. These are sensory afferents within the joint structure itself, and they might be involved in sensing things like the stress or strain within the joints. And this is the role of joint afferents in general has been controversial in the nervous system, in neural control. So it's clear that these afferents can convey information about the state of joints. Okay, the degree of that information isn't always clear, but this is just the firing rate of a joint afferent as you impose a stretch within the knee joint itself. Okay, and you can see that it modulates its activity accordingly. Okay. We know that interneurons in the spinal cord receive these joint afferents. So these are the 1A, 1B non-reciprocal inhibitory or non-reciprocal interneurons in the spinal cord. And if you stimulate a joint afferent, at a particular point, can evoke a PSP in these neurons. We know that if you stimulate joint afferents, you can do things like reset and entrain the CPG in fictive locomotion, right? So if you stimulate a joint afferent, you can reset the phase between flexion and extension in locomotion, so they have access to the CPG. And then there's these experiments that were done in the 80s, which were suggestive, where they did these experiments in cats, and they put in local anesthetic into the knee joint. And what they saw is that some animals, they showed a very strong change in their behavior. So these animals that actually put their foot down flat on the ground, whereas in normal, you'd always be up on your toes in digigrade locomotion, right? So there are some animals that seem to have this very strong effect, right? But this wasn't really followed up and didn't to see how robust this was. So what we wanted to do is basically just continue this and ask whether, in particular, we could find evidence whether the strong correlations between VM and VL might be due to afferent activation, right? That's sensing essentially the load on the patella and then regulating the balance of activation between VM and VL, right? So to do these experiments, the idea is we're just going to inject lidocaine into the knee joint. Okay, and we did experiments here recording from multi-unit activity in the articular nerve. This is the medial articular nerve that conveys the joint afferents from the knee joint. And without any lidocaine, we just tapped the patella here and saw multi-unit activity. We put on lidocaine and repeated those taps and basically saw no activity at all. Okay, so this was able to suppress the activation of joint afferents going in. And we looked at the spread of the dye. It stayed within the joint capsule. So remained within the joint capsule and got the entire structures. And so the logic here is just really straightforward. We're just going to have animals do locomotion on a treadmill, and then we're going to either inject lidocaine, we're going to look at baseline activity, do an injection of lidocaine, and then look at their behavior after the injection, or we'll do a sham control to kind of go over the same, control for the effects of time and so forth. So the first thing to say is that we saw really no change on aggregate behavior, right? So if we looked at the overall, these are the average EMGs of our quadriceps muscles. So the black is the activation profile of our muscles before the lidocaine. The orange is the activation profile after the lidocaine. And we saw no significant systematic differences across these activations, right? And these are just down here, I guess, I'm sorry, the x-axis isn't labeled very well, but these is the activation of each of the 4 quadriceps muscles, okay, in the different conditions, okay, before and after locomotion. I think actually, I take that back. This is one muscle, 2 muscle. This is VM, VL, VI, RF, and these are taken at different time points during the step cycle for their activation. Sorry. So we saw no difference between VM and VL or between these muscles before and after lidocaine. Okay, so there's really, and same thing for the kinematics, we saw very little change in overall behavior. And now we go in and look at the correlations between these muscles before and after lidocaine. And what we saw first off is that the correlation between VM and VL was basically unchanged. Okay, so this active correlation between VM and VL that we saw that was high, during locomotion remained high even after suppressing the activation from lidocaine. Interestingly, what we saw is that the correlation between other muscles, between VM and VI or VL and VI, that correlation actually went down. Okay, so first off, this was nice for us because it gave us a nice positive control to say that our lidocaine was doing something and was changing behavior, right? But it does suggest that somehow these joint afferents are having a role in specifying the correlation structure. And interesting, the correlation structure changes even though the average activation doesn't change. Okay. But nonetheless, it suggests that this preferential activation of VM and VL was not driven by joint afferents, right? And then if we did our sham controls, this is just injecting lidocaine into the joint, not lidocaine, saline into the joint. We saw no change of our correlations at all across these conditions, okay? So it suggests that this correlation between VM and VL is not being driven directly by joint afferent activation, okay? So at least in this context of this kind of normal behavior, this correlation between VM and VL, it suggests that this joint afferents are not driving those correlations, that coordination structure. And so what we want to be asking in our next experiments is what might be doing this. And so a few possibilities is one that it might be driven by muscle proprioceptors, right? So even though muscle proprioceptors will not directly monitor the state of these internal joint structures, you could imagine that the nervous system could understand the relationship between a force in the muscles and their effects upon the internal joint structures, and therefore estimate the state of these internal structures by monitoring proprioceptive activation instead, or proprioceptive activity instead. And there's some really neat work by people, by Eli Zalzer in Israel, who's done work kind of showing when you knock out muscle proprioceptors, it actually causes joint deformation, changes in joint structures and things, which might be suggestive of this possibility. Another possibility is that this correlation between VM and VL might be specified entirely feed-forward, right? So it might be something that's hardwired into intraneuronal systems, which activates motor neurons to VM and VL and kind of hardwires this correlation between the two. And then the adaptations you might see when you put on a load might reflect modification of either the synaptic strengths or different activation levels that modulate this balance between these two. So these are kinds of experiments that we wanted to get to next and look at, and then moreover, even if joint afferents don't play a role in this kind of moment-to-moment correlation, maybe they play a role in kind of more long-term adaptations, right? So when you have things like when you have an ACL rupture or damage to the muscle, maybe it's only those kind of sustained changes to the afferent activity in joint afferents that kind of drives those adaptations. And so those are things we're also looking at as well. So overall, I think what we've kind of shown is that we've provided evidence that joint stresses make a difference, at least to rats, right? So this is what our work has kind of showed, is that in our animal model here for quadriceps, these joint stresses and strains play an important role. I think what's an interesting question, and it's part of what we're doing in this NeuroNext, is asking things like this, will this be the same across different scales, right? And so if you just think about, rats are kind of, they have a pretty significant, not trivial mass. But if you went down to something like a Drosophila, right, it has limbs and things as well, but there the mass and the forces that are involved in those kinds of behaviors are significantly less, right? And so maybe the internal joint stresses are not so much of an importance in driving the coordination pattern there. Whereas when you get to rats or cats or humans or horses and elephants, because our forces become that much larger, maybe these internal joint stresses become much more important. And I think an interesting question is, will this kind of this balance between task performance and internal stresses and strains remain consistent across? And it'd be interesting to hear people's thoughts on this. We have a lot of people, experts in Drosophila and other things here as well to understand that. So I just want to finish up again by acknowledging, again, this is Cristiano Alessandro and Felipe Barroso, two really talented postdocs who did most of this work. We've also continued this work with Gilles Sarncoli, who's a really talented biomechanist at Barcelona, who's been doing some of this kind of helping to continue this modeling. And then also we've been doing this work again in collaboration with people like Roger and Hillel and Fletcher Young and others who have been continuing this work as part of the NeuroNext project in general. And then just also to acknowledge our funding sources. So thanks for your attention.
Thanks, Matt.
Thanks very much, Matt. That's very nice. We have now time for questions. I see Greg showed up, so we're all happy about that.
Actually, Roger, we have about 4 minutes for questions, and then we would have our break. So
yeah, right. So we have time for a couple of questions from Matt. Nick Shushensky has raised his hand.
Yeah, Matt, wonderful talk. I really, really enjoyed this. Thank you very much for sharing all this. So I have an ignorant question as someone who knows very, very little about vertebrate anything besides what I know from being one myself. Are there sensory structures embedded within the bone that can more directly sense, for example, stresses in the bones, or was that covered within the umbrella of joint proprioceptors?
Yeah, it's an interesting question. I mean, I've looked at it. So there definitely are afferents within the bones, but their role has not been very clear. And I think that in general, the idea is that the consensus is that they don't seem to provide much information as far as instantaneous loading. People have not looked at them. They've looked at them in the context of things like bone repair and things along those lines. It's often where you see it come out. I think it's a bit of an open question, just because these are really hard. These are unmyelinated afferents, and getting really good recordings from them and looking at it in conditions has been really tricky, and identifying where they're coming from has not been totally clear all the time. But I think the consensus that people have looked at it kind of said that you don't see much information, much sense for that, I suppose. They're there, but do they actually convey that information is unclear.
Yeah, no, thank you.
Yeah, thanks.
Hey, Paul, would you like to ask a question?
Yes, I have a question, and it's great to see you all. So wonderful presentation, Matt. Thank you. Now, you started out by putting this context of rehabilitation, where you actually mentioned this point of what's called true recovery, right? So that the kinematics of movement before and after a rehabilitation or a lesion to the brain, for instance, would actually be identical. Now, in some sense, with your results, we must be able to actually say something about the plausibility of that hypothesis, because in the field of rehabilitation, there's a counter movement, right? It says, no, it's more about recovering function than the details of kinematics. And with your results, you could actually also support that point of view to say, look, with these kinds of perturbations, to really restore the identical kinematics might actually be a rather great challenge. So how do you look now from your results, now that we went through it in detail, how plausible do you still find that hypothesis of true recovery?
I mean, I think I would say that, I mean, the suggestion from our work, and I think what I believe is that the best thing to do after rehabilitation, depending upon the injury, is not necessarily to do what you did before. I mean, I think that's kind of, and so that I think there's also work that, one of our collaborators initially in the work was Yassine Dyer, who has looked at kind of stresses on, again, the contact between the femur and the tibia, and showing that when you do reconstruction of the ACL, it actually changes where the stresses are across those two. And so that if you were to just do what you did before, you're going to end up at a part of that, the cartilages, where it's actually quite thin, and you're going to lead very naturally to osteoarthritis, right? And so, very clearly from that point of view, you want to choose different activations to shift that contact point. I think the challenge, though, and this is the challenge of looking at kind of these internal joint variables in general, is that estimating them or monitoring them in any kind of real ongoing behavior is very difficult, right? We can't put sensors in to measure these contact stresses or the joints, joint strains and things to actually know, is what the person's doing, is that good or is it bad? And instead we have to go through really complicated biomechanical models to kind of estimate these variables, which then depend upon the accuracy of those models to do that. So I think that, our work, I think what it does is kind of says, hey, pay attention to these, and that you want to not just force people to do what they're doing before, but recognize that that might be jeopardizing things. What our work doesn't do, and I think which should be challenging, is to say, oh, but here's what you should do. That's a much harder thing to kind of say, and to recognize whether what the person is doing after an injury, is that good or is it bad? I think that's a hard thing in general to be able to say. So I think that's still a challenge to be able to that point.
Right. Well, we're going to hear the solution that next year. Thank you.
Thanks.
Very good.
Thanks for the questions.
So we're actually due for a break right now. But I
Well,
really
let's-
want to hear what Ansgar is.
Yeah, let's have the Ansgar his question and then we can have the break.
Yeah.
Quick question, Matt. This is also a bit ignorant from an insect invertebrate researcher. Is it possible, because what you show with your experimental modification in the knee joint will affect the 1A1B balance of both VL and VM? Is it possible to get a hand on, for example, H reflex-like individually for the subpartitions of this group of muscles, so that one could actually look at that, at adaptations?
Yeah, I mean, those are the kinds of things we want to try to get at. Essentially, is kind of the what are the structures involved in this control? Like, what are the neural systems? Are they classic reflexes, or are they something separate and aside? There is some work, we've talked with, like Richard Nichols and looked into his work, and there's some evidence that are some of the structure of the reflexes that he looks at in terms of force sharing across the quadriceps would be consistent with that idea that you could have things that, again, the force sharing doesn't necessarily make sense in the context of their knee extension actions, but if you think about their medial lateral loads on the patella, it begins to make more sense in terms of those structures. So those are the kinds of things we want to try to get at.
Thank you.
Yeah, thanks.
Okay, so we're going to take a brief break. We'll be back at 9:45. Our time.
45.
Sorry. We'll be back
Yes.
in 7 minutes. Sorry.
Yeah, 7 minutes,
minutes.
45 minutes beyond whatever hour you are at.
Yeah, that's it.
All right, look
See you
forward
in
to
7
seeing you. all.
minutes.
Right, see you in just a few minutes.
Thanks, Matt. Good work.
Thank you,
Thanks,
Matt.
Thanks, everybody.
Hi, hello.
Yeah,
So-
hey, good, Roger. How are you?
Let's go with Greg next, and then we'll be back on track, right?
Sounds like an excellent idea. All right. So it's
Okay.
45 minutes past the hour. And so we will continue our workshop. It gives me great pleasure to introduce Professor Gregory Sutton. Greg received his undergraduate degree and his PhD from Case Western Reserve University in mechanical engineering. He then did postdoctoral fellowships with Malcolm Burrows at Cambridge University and with Danielle Robert at Bristol University. And he is now a full professor at the University of Lincoln in the United Kingdom and has a university research, Royal Society research fellowship. And he has been doing fundamental work on the biomechanics of animals for many years. So I look forward to hearing what he has to say. Greg?
Okay, so here we go. Hold on. Screen share. Now why slideshow from beginning? Okay, can everyone see my slides?
Yeah.
Okay, so I'm going to talk about limb control parameters and how they're almost completely determined by the size and the frequency of the movement. So I'm going to start at the beginning talking about the science of animal locomotion tied to the horse galloping done by Edward Muybridge. In 1872, he filmed the gallop of the horse, and there was to figure out if the horse hooves ever left the ground, and at the same time, and this began the science of locomotion. And there was a lot of question on what were the important parameters for controlling this motion. And as we in this seminar are very aware, there's an army of parameters that tie to the control of this motion, and it is very complex. But one of the initial ways to analyze this, to analyze locomotion in the horse, was put together inspired by fluid dynamics. And it was inspired by, this is Williams Froud, and he was looking at cresting of waves. And he wanted to know if you had water, when it would move in a crest, would the wave crest or would the wave stay low? This wasn't tied to surfing in any way. He was working with the Royal Navy. So if you look at the particle of water, there's two forces on it. There's the mg pushing down, and then there's the centripetal force as the water goes over the wave, mv squared over L. And the ratio of these two forces is the Froud number, and a high Froud number is the centripetal forces will carry the water up and over to crest the wave. And at low Froud numbers, the centripetal forces aren't larger than gravity, and gravity will keep the wave from cresting. Neil Alexander attached this to looking at locomotion in horses and said, well, we can do this exact mathematics on the parameters of a horse and ask, will the center of mass of the horse crest over its leg, causing it to bounce more, or will it stay on the ground, causing the animal to do more of a walk, the center of mass stay more level? And this was an incredibly informative way to quantify horse locomotion, with the Froud number being a really good way to quantify the different gaits, walking, trotting, and galloping in horses and cats and humans. It's a wonderful way to look at different locomotion strategies inspired by fluid dynamics. But the Froud number makes a prediction that a horse at full gallop going 7 meters a second will be dynamically identical to a mite moving 100 centimeters a second. So in 2000, i.e. these mites moving it, if you could find a mite moving 100 centimeters a second, the mites would gallop in the same way a horse would. Now a mite, this was filmed high-speed camera in 2016, and this is a mite, high-speed film, moving 100 centimeters a second, and it is doing nothing of the sort. So there is something going on with the Froud number that works great for horses and cats and dogs and humans, but it doesn't work at all for mites. So I'm going to start by looking at the model, a simple model of the horse leg swing, where you have a leg swinging. I've got the leg swinging from 30 degrees extension to 30 degrees extension, about 1 second per cycle. And you look at the muscle forces applying joint torques. And in the middle of the swing, the muscle forces are 0 and the leg angle is 0. But the muscle forces and the leg angles are out of phase. And this is because of the mass of the leg and the interaction of the mass of the leg and the joint forces. So we have an example cyclic behavior just of horse, which is an example for a large animal. And there's an acceleration of the leg from the joint forces, and then the joint forces have to decelerate the leg to break it and to cause the leg to break and stop moving. And that creates this out of phase motion, out of phase relationship between the joint torques and the leg angles in the horse. Now, if we want to look at something small that also has cyclic motions, I'm going to use an example of Aplysia californica. This is a sea slug, and it's got a mouth part that moves forward and back at in about 3.5 seconds. It's a slow motion. And there's a group of muscles that move this central odontopore structure forward and back in the same way that a horse leg moves forward and back during a locomotion cycle. So you can model this with the muscles pulling against the springs and get a activation of the muscles up top here and the position of the odontophore bottom here in red. And in the middle of the motion, we're in the horse leg, the forces are 0. The muscle forces in the Aplysia swallow are about half their maximum level. And at the maximum motion of the Aplysia mouth part, when it moves forward, the muscle forces are at their maximum when the muscle is moved forward, when the structure is moved forward the most. And when the structure is moved back the most, the muscle forces are at their minimum. So whereas the horse, the muscle forces and the motion are out of phase, with the Aplysia, the muscle forces and the motion are completely in phase. So this Aplysia motion is also very slow, it's sludgy, but in my modeling of the motion, I don't have any damping. So we have this slow motion with a very sludgy aspect to it, but there's no damping, but there appears to be no oscillations. So is there actually oscillations? Is there damping in there somewhere that's not in the model? Or how can this Aplysia motion be sludgy with no sludge? And if you zoom in, there's actually small vibrations in the model simulation that are caused by numerical error in the simulations, but the small vibrations aren't biologically relevant. And the reason why is that the system, when you have a small, slow-moving system, its resonant frequency is very high. For the Aplysia, it's 14.2 hertz, but the driving of the muscles is 0.029 hertz. So you end up with a system that moves very slowly. Any oscillations are incredibly fast, incredibly small, and are damped out by any damping whatsoever. So what we have is the Aplysia is moving in a slow sludgy motion, but it's a special kind of sludgy where it's not sludgy because it's viscous, it's sludgy because it's small. So these small systems have an intrinsic slow sludginess to them that is just because of the high resonant frequencies of the system relative to slow muscle driving, slow muscle driven motions. So what we have, so if we look at this in terms of the energy, with the Aplysia, if we look at the amount of elastic energy that's stored in the tissues, and compare that to the kinetic energy, the elastic energy is about 0.8 millijoules of energy. The kinetic energy is 0.00015 millijoules. This system is so dominated by muscle work going into elastic energy that we can ignore inertia and we don't have any overshoot, we don't have any major oscillations. So this ratio, so this gives us a way to look at these slower motions as a ratio of the kinetic energy to the elastic energy. And for the Aplysia, it's about 1 to 6,500, whereas for the horse, it's about 1 to 1. So what we have is two motions that are both oscillating. One of them, the horse has a cycle time of 1 second. The Aplysia has a cycle time of 3.5 seconds. The fundamental difference is their size, but the motions are mechanically very different. And the question is what is so different about these two motions, despite the fact they're both oscillatory over about the same time scale? So Nick Szynski and I decided to quantify both of these motions with one basic model. So we have a basic model where we have all of the input forces, the muscle forces, any actuator, the things putting energy into the system we put on the left, F, and on the right, we have where all the energy goes. And the energy can go into either kinetic energy, which is proportional to density times length cubed. We can do that scaling, and the scaling of the kinetic energy is density length to the fourth over time squared. We can then look at the elastic energy, Kx, which is proportional to stiffness, Young's modulus area over L, or Young's modulus times L. That is proportional to Young's modulus times length squared. And if you look at the relationship of these two terms, the difference between these two terms is length and time, how long the thing that is being moved is, and what is the cycle time over which it's being moved. And that gives you the relationship between the inertial energy and the elastic energy in the system. So if you're big, if you're big and fast, your lengths are big and your T's are small, you get a lot of inertial energy. If you're slow and small, your inertial energies are incredibly small, your elastic energies are much relatively larger. Now, I'll talk about damping as well. We will put that in. So we leveled the playing field by thinking of just a general limb, just one limb that is being moved back and forth by the muscles with this one equation of motion. We reduced it all to torques to move it rotational. The torques change the units, but they do not change the relative relationships of the parameters. And we can still look in terms of kinetic energy, damping energy, and elastic energy. Then we could look in the literature and parameterize our constants for mass and damping and elasticity based off the scaling relationships in the literature. And it turns out that animals are pretty much made of very similar stuff. So the density is the density of water. The elasticity of muscle tissue is very similar for whales and for insects. And the damping, there was a Garcia paper from the Full Lab where they found that the damping also scales quite linearly or quite constantly over animals, which allows us to parameterize the model and drive it at different frequencies and look at where the energy is going. And we still have this model where we're looking at the things where the energy is going, and we don't yet care as to what's generating the energy. So what I'm going to say is true whether these motions are generated by muscles, heel muscles, cross-bridge models, motors, electric fields. Anything that adds energy to the system is just on the left. I'm just asking, where is the energy going? So where is this energy going? We have two variables, the length of the limb and the frequency at which it's moving. The length of the limb is on the y-axis, frequency on which it's moving. And we can look at where the energy is going in the most kinetic energy, which I will show in yellow, viscous damping energy in orange, and quasi-static elastic energy, or in civil engineering, this is called quasi-static motions, elastic energy in red. And this is the space of the plot, where for large, fast motions, the energy is mostly inertial, mostly 1/2 mv squared. For small, very fast motions, it's mostly damping energy. And for small, slow motions, it's elastic, quasi-static energy. And for slow, large motions, it's elastic energy. So we've got the kinetic energy, damping energy, mostly potential energy, two variables. Now, this graph actually tells us a lot more about the behavior, a lot more about the limb. The resonant frequency of the limb is this black line here, where it's behaviorally relevant. The resonant frequency doesn't mean a lot when everything is very, very viscously damped. Critical damping is at this dashed line here. So everything above this dashed line, the motion is underdamped. Everything below this dashed line is overdamped. So we know how stable the behavior is as well from this graph. So we have 5 regions of this graph. Each is a function of the size, just the size and the cycle time of the motion. And that tells us almost completely what is the mechanical regime that this motion is under. So in our first region, kinetic underdamped, this is where horses galloping is. The energy is going into, the muscle energy is going into kinetic energy. Inertial forces are dominant. And the force and the displacement are 180 degrees out of phase, like in the horse galloping example. Now, if one of these systems is perturbed, if something happens to the limb when it's moved, these perturbations require active damping to remove. The control system has to do something to restore the joint to its initial position because the passive dynamics won't do it. And in this kinetic underdamped world, the inertial forces and kinetic energy are the dominant players in the scene, so that a Froude number, which is a ratio of gravity to centripetal forces, is a very important number. So if you're in the kinetic underdamped realm, Froude number is the thing to go. If you're large and slow, this is quasi-static motion. Your muscle energy is turned into potential energy, elastic potential, and your force and motion are in phase with one another, like the sea slug. So your muscle force and your motion go from out of phase to in phase, and these perturbations of the system are small problems. There is enough momentum to create some carry on of perturbations, but because of the slow speed of behavior, they can be navigated relatively easy by the nervous system. And this is like a large elephant trunk motion. Large elephant trunks moving slowly is a quasi-static underdamped behavior. Now for the bottom right, we have quasi-static overdamped behavior. All of our energy is turned into elastic potential, just like in the large quasi-static case. Force and motion are in phase, just like in the large quasi-static case, but perturbations can be completely ignored because the system is so mechanically stable that any perturbations are restored to are removed from the system incredibly quickly relative to the time scale of the motion. And this is the emotion of the movement of the aplysia feeding apparatus. So perturbations, this kind of system, completely ignore perturbations. Don't worry about it. Now in region 4, small, very fast motions, the energy is almost completely damped out by viscous joint forces. There's a lag between the force and the motion that's neither 100% in phase or 100% out of phase. Perturbations are viscously damped out, but they take a lot of time. And this is where that mite running is, that the mite is dealing with large viscous forces within its joints, and the inertial forces and the gravitational forces, while having the same ratio as the horse, are both damped out, are both swamped out by a much larger unmeasured quantity, the viscous forces, which is why the mite is moving very, very differently than the horse, despite the fact that they have a same Froude number. And then this last region we found was the kinetic overdamped region. This is for a small section of fast moving motions of an intermediate size range. And going through the literature, we only found one motion that fit this range. There's still a phase lag between the force and the motions, but it starts to approach the antiphase of the inertial realm. Perturbations are viscously damped out, but inertia has to be considered. And the only motion we could find in this range was a Morse code operator, telegraph operator moving his fingers at the highest rate. So this allows us to quantify, we can put various behaviors, locomotion behaviors, grasping behaviors, movements on this graph and see where they exist in the kinetic energy, elastic energy, or viscous energy zone. We can also look at the ultimate stress that this would put on the representative muscles here to show no-go regions where the biology can't go due to that. This would damage the muscles or damage the bones. And we can see that, and this is every single flex in the literature. So this is the flex graph. And while the horse and the mite have the same Froude number, they exist in completely different zones mechanically, with the horse locomotion being in the inertially dominated zone and the mite locomotion being in viscous dominated to viscous elastic dominated. So they have the same Froude number, but they are in different mechanic zones and thus are very different. So we've got the three zones, F equals MA dominated behaviors, X equals KX dominated behaviors, and F equals CV damping dominated behaviors. So about this Froude number, we have the horse and the mite that have the same Froude number, but very different locomotions. So is it possible that there might be a way to improve classification of movement that takes into account these effects, but takes into account the different partitioning of energy, but doesn't require any more deep parameterization of the existing data. So if we look at the different zones, for example, if we look at the quasi-static zone, for the inertial zone, Froude number works great. Quasi-static zone, if we compare the aplysia to the elephant, for instance, we've got the elastic forces that increase with L, the gravitational forces increase with L cubed. We can't use the Froude number to parameterize this because the Froude number is about inertial forces. So what if we rederive another dimensionless parameter instead and look at the ratio of the elastic force and the gravity? Well, this is E over L over rho G L cubed, simplifies down to E over rho over L. And turns out E over rho is a parameter that's already in the literature. It's called specific modulus. So we get a dimensionless parameter within the quasi-static zone that tells us how does gravity relate with the elastic forces in the joint, which is specific modulus divided by L, which is really nice and easy to calculate. We've got the specific modulus divided by L, which tells us what's going on in the quasi-static realm. We've got the Froude number, which does a great job telling us what's going on in the kinetic realm. Going from the kinetic to the viscous realm is the ratio of inertial energy to viscous energy, which is a Reynolds number. So there's already a dimensionless number to quantify transitions from the inertial zone to the viscous zone. And then the transition from the viscous to the quasi-static, there's already a dimensionless number for that called the Deborah number, which would be the use of two fluid numbers that are used for fluid analysis to define motion, the same way we use Froude number today. And then across the boundary between the quasi-static zone and the kinetic zone, this sharp boundary is the ratio of elastic energy to kinetic energy. That happens to be Cauchy number. So what we have is a group of dimensionless numbers that can tell us how the energy is distributed within a different locomotion or movement, and we can quantify the stability and the energetics of the movement based on this new set of dimensionless numbers that can also all be boiled down to one parameter that this is all correlated with the phase between the muscle forces and the motion, so we can actually map these on top of the phase of the motion. So we have a map now of the way to dimensionlessly analyze a motion and compare different motions that takes into account that mites and horses move very differently despite moving at the same Froude number. So if we think about muscle forces, that is all on the left of the equation. Muscle properties, feedback, motor control, all go here. That allows us to, using length and time scale, we could map the properties of a given actuator on our energy plot to show the interaction between actuator and energetics in the final motion. So that is a thing we can do in the future. This kind of mathematics is completely doable. And for feedback, positive feedback is not very often, it hasn't been seen in the large vertebrates. And if you add positive feedback to an inertial system, it creates massive instability. And as I've shown in the plot, stability is a problem in the kinetic dominated realm anyway. Whereas positive neural feedback is seen in the smaller insect systems, but they exist in this quasi-static realm where positive feedback, where everything is very, very stable and positive feedback won't cause instability. So this informs what is the neural feedback of the system. And also informs what the sensors would be for a system with the kinetic dominated behaviors. You would want something like a Golgi tendon organ to measure forces. while the system is moving because you want to measure forces and accelerations. But in the quasi-static, you would want something to be much more keyed to positions such as campaniform sensilla. So that is my talk. Are there any questions? I can't.
Thank you, Greg. This is wonderful. We have 10 minutes for questions and discussion. It's a lot of material, so if people want Greg to go through certain things that he presented, again, you're certainly welcome to do that. And if you have questions about the implications for your system, please feel free to ask. Greg, since no one has jumped in yet, let me just ask a little bit more about the feedback question. Could you go back to that for a second?
Oh, and there's a question from Steve.
Yeah. So let me just go back to the feedback, and then I want to hear Steve's question.
Okay. Tell me about the feedback. Well,
Okay. So can you bring up that slide? Is that
sure.
okay?
Will do. Which feedback? The positive feedback or the sensors? The positive.
Positive feedback. Okay. So as you go through the transition, that's particularly interesting because what I would suggest is if you have a large limb with lots of inertial properties, as it moves more and more slowly and moves into the quasi-static regime, feedback could change in terms of how important it was or even the sign it would have. Do you want to comment on that?
Ooh. So this would imply that the feedback, the important feedback of a limb would change as a function of the limb's speed. Now there's a really cool consequence to this so this is one of the things that I've been playing around with my head, is that if your limb's moving fast, you'd want the second derivative of things to be fed back. You want the forces and accelerations. If the limb's moving incredibly slowly, you'd want the zeroth derivative of your position. You just want the position. If you want the nervous system, if you want a nervous system perfectly keyed to feedback, you'd want a system that was able to transition from second derivative continually to zeroth derivative across the speed of the motion to get the most important derivative of the motion for your feedback. In theory, this could be, there's a point where you'd want the first derivative and the point where you'd want the 0.5th derivative and the 1.5th derivative, which are regarded as hypothetical, but there are people who've been studying feedback in neurons that say some neurons are actually giving a 1.5 derivative of feedback or the half derivative of feedback. So this would tie to that, and that could create predictions of what would the derivative of the best feedback be. What would the feedback be of the best derivative of the motion relative to the speed of the motion? And could you look for that in the neurosensory neurons that are presenting the intermediate derivative feedback information? But that's a little bit out there as a hypothesis.
Fantastic. Okay, let's call on the people who are asking questions. Steve?
Hello, can you hear me?
Yes.
Yeah.
Okay. It's just a to sort of listen some comment. It seems you've got a mixture of things which move horizontally in terms of your dimension numbers and things which change vertically. Now the horizontal ones are to do maybe with things changing gait, but the vertical ones, if it moves up and down, and possibly more to do with development and how things change as they get bigger.
Yes.
So our question is, what is the implications for changing control in an animal that say can go through a lot of gait changes? And I guess anything can go from standing still to walking, which is always going to be a quasi-static element, maybe moving into another realm, versus these vertical transformations which may occur as an animal develops.
So it would predict that. So the animals that move vertically from the very small to where inertia is important, say very small mice, for instance, that are fully quasi-static at their smallest, but very large rats can get semi-inertial. It would make a prediction that their feedback, their neural sensory apparatus would change as they get bigger, and that their mechanical control would also change. There's some evidence of this in humans where our gaits, small children have very different gaits than adults. So There's evidence of that in humans. I don't know of that much analysis of changes of gaits in insects as they get larger or smaller. That I don't know.
I mean, I was thinking something maybe like a nauplius larva in a crustacean, which proves, I mean, some crustaceans go through generally enormous changes in scale.
Yes. Oh, lobsters would be great to look at because they go big and very small. So
Thank you,
does that
Steve.
answer your question, Steve?
Yeah, I think we should go on. I think we should go on. Ansgar, I think you have a question?
Yes, talking about positive feedback, Greg, you obviously relate to false feedback, or?
Yes.
Okay, because which would hypothesize that you would not find in the fruit fly similar false feedback, positive false feedback that you will already find in an animal like a stick insect or a larger insect.
No, the fruit fly is small enough and stable enough to get positive force feedback.
Okay, yeah, okay.
I'd hypothesize you would not find it in a horse.
Ah, good. That's not my experimental animal, but still, okay.
Okay, so
yeah. No, thanks a lot.
Okay.
Okay, I think Matt Tresh.
Matt?
Yeah, really neat talk. I was kind of wondering, maybe follow up on kind of the previous comments, like thinking even within an animal or an organism, you have very different masses and properties, right? So if you think about going from digits to proximal muscles or to axial muscles, the masses that are associated with that and the importance of connective tissue and so forth changes quite a lot. Have you thought at all about how that would work? Do you think about, would it be one uniform control across the entire limb? Or would you actually have different controllers or different segments according to the scale that they're operating?
Okay.
And speed could change as well.
Okay, so this is where I'm going to go out. Okay, so there's how I think it's working is the control of a quasi-static motion is so relatively simple and easy. My hunch, so this is just a hunch, is that everything is built on a model of quasi-static control, that is the primitive for controlling emotion. And that if you can control it with quasi-static, the nervous system controls it with quasi-static. And my suspicion as I go more out on the limb here is that if you look at control of inertially dominated things, the inertially dominated motions have a quasi-static system that's been changed to take inertia into account. And so that when looking at control internally to the body, anything that can be controlled quasi-statically, I think is controlled quasi-statically, like the human tongue is a quasi-static system. And that the limb motion is more complicated to control, and that there'll be a separate additional feedback systems for that the tongue wouldn't have. This is completely a guess on my point of view. So this is
cool.
As you will.
Roger, I think you have a question.
Yes. Okay. So everything you showed us, Greg, was for swing, for unloaded motion. So if you went to stance, there's a lot.
Yes. There's a lot on stance. Yeah.
But in terms of positive feedback, will you have the similar conclusions about large and fast, the kinetic region, also positive feedback being bad for force, or does it make sense to have positive feedback there?
So for the stance, the preliminaries we've got on stance argue that it would be pretty terrible for the large animals, but okay for the small animals to have force feedback. That's the preliminaries. There's a whole there's a whole other talk on the stance, because that's the energy allocations are very similar, but you have this when in the viscous zone, you end up getting more mass dominant stuff, but the quasi-static stuff still holds for stance. So.
Well, this is wonderful. We're right at the correct time to end our session at this point, and then this gives us a full 10-minute break. So So first of all, thank you again, Greg, for a wonderful talk and great answers to questions. Our next speaker will start in 10 minutes, 20 minutes actually, no, our next speaker is, I guess, going to be starting right now, Matthew. So Roger, do you want to introduce Matthew?
Yes. Yes, I would like to introduce Dr. Matthew Chardon. He's a research assistant professor at Department of Neuroscience, Northwestern University. He received his PhD from Northwestern in 2015. He does computational work, so really interesting computational work, and I'm greatly appreciative because he's helping one of my students explore parameter space in a simplified spinal circuit. So please, Matthew, take it away. We have Matthew.
I see him listed, and I see
I'm here.
Okay, here we go.
Hi.
Yes.
Thanks for the introductions, Roger. Let me make sure I do this correctly. Okay. Are you able to see my poster or my talk? Yes. Okay.
Yes.
Perfect. Hi. So basically, I'm going to try to tell you a story, and I hope you enjoy it. But basically, it's a story through my own struggles with the inverse problem of Hodgkin and Huxley equations, and how I think we might be moving in the right direction to try to find their parameters with respect to measured data. But just before we get started, I wanted just to give everybody an overview of what our lab does. Basically, we're interested in spinal cord circuits. And there's, two main avenues. One is, therapeutics, obviously, to try to stimulate the spinal cord to get, to affect autonomic system or locomotion systems or pain. And then there's another one, which is a little bit more subtle, which is if we're able to reverse engineer the spinal cord, well, maybe we can, in the future, create kind of a spinal cord chip out there that could be able, that'll be able to integrate the thousands of inputs that the spinal cord integrates, and then make a quick decision on what to do. Usually your gate takes about 50 milliseconds to resolve. So perhaps if we're able to design these chips, we'd be able to solve these very complicated problems very quickly. And so I'm jumping in straight into what we believe our approach should be. So basically what we're doing is we're looking at a bottoms up approach. So we started to look at the simplest possible loop or circuit in the spinal cord, and that would be your reflex response. And so that's the 1A that attaches. So if you look at the image on the right, that's basically everybody can focus on the green alpha motor neuron here. So you have the U1A connecting to your alpha motor neuron back to the muscle. And so that would be your simplest controller. And so what we decided to look at is at the a little bit higher level, which is we believe to be, the reciprocal and the current and the recurrent pathway or network in the spinal cord. And this is, the simplest possible circuit that we think can control a single joint at this point. So we're trying to reverse engineering this neuron. And so here I'm reverse engineering this this circuit. And the reason we want to do it, it's fundamental for locomotion. We have a lot of knowledge about it, so it's easy to do the reverse on it. It's accessible. We can stimulate the 1As, and then it's composable. So we think it's repeated throughout the spinal cord for many different joints. So what we started to do is, with all the data that we have, is to try to do this reverse engineering at the single cell level. So looking at the alpha motor neuron itself, and then possibly adding, working our way back to other cells, such as the Renshaw, the 1A interneuron. And so the problem we started to see is, while doing the literature research, is that there's this multiple realizability, which basically it's the dilemma of the many different possible solution sets that that one can find. And so so Prince and Al found a, indistinguishable network activity from widely disparate deterministic models, and so forth and so on, and all the way to Alonzo Marder, which is basically the model I'll be talking about a little bit more today, which just shows basically that a neuron can produce similar neural activity from multiple sets of conductances, which is basically flips on its head the notion of reverse engineering, or not flips it so much as to makes it more complex. And so we started to look at different methods. And so we looked at computational approaches. And so, there's a bunch of them out there, but they all suffer from the local minima problem. And I'll try to motivate that in the next few slides. And the other thing is it only provides a single parameter at the end of the search. There's these machine learning techniques. It's just, artificial neural networks, Gaussian mixture models, deep learning, and so forth. And those need large data set, which we might not have. And the posteriors, which I'll get to, are estimated in this. So, and then there's this third method. So we start to look at statistical methods, and these methods don't suffer from the above issues, and they've been relatively unexplored in this space. And so I'm going to try to argue that these methods are a great path forward to try to do this inverse, parameter search for the Hodgkin-Huxley equations. And so just to do a little quick review. So basically, we're going to be using the Bayesian equation as the centerpiece. And so what we're looking for here is the posterior, which is the probability of your parameters given your data. And that's basically on the left side of the equal sign. Then the likelihood, which is the probability of your data knowing your parameters. And so that likelihood here is, as I will show you, is our cost function basically, or a loss function. And then the interesting part about this equation is also you have the prior to the right, which is basically probability of your actual parameters that you've chosen. And so this is where experimentalists can come and give you a sense of what the parameter sets should look like prior to doing a search. And then the probability of your data underneath, that doesn't really matter, and I'll show you why in the next algorithm. So basically, you plug in the Bayesian inference inside this Markov chain Monte Carlo method. And so if we go back to, we can follow this loop. And so the idea is this. So basically what you do is you propose a set of parameters that you plug into your neuron model. So this is where your Hodgkin-Huxley equation is solved. And then you also have your recorded data on the right here. And you'd subtract the two, which gives you your likelihood. So that's the third step. And so then you take your prior and your likelihood. So the prior, which is on the very left, the information about your parameter values, and you multiply that with your likelihood, and that gives you your posterior sample. And so what you do is then you have to make a decision. Should I keep this posterior? Is it better than the one that I had before? So should I keep it, or should I reject it because it's worse? And so this is where this fourth step comes into play. And to do that, you divide basically you divide the previous posterior to your new posterior, and if it's above 1, that means it's better. And that's where I was talking to you about the probability of y. That's where it disappears, because you do the division. And so you run this loop over and over and over again until you, I guess, as long as you think it worthwhile, and then you start to get these posterior distributions that's on your output of that algorithm. And so I'm going to try to illustrate this with a toy model. And so the classic model that we that we wanted to, that everybody knows, is the Hodgkin-Huxley equation model that has a sodium potassium leak model. And so as a proof of concept, we considered the inverse problem, where the goal was to recover the sodium and potassium conductance in a symbol model, right? And so we demonstrated this by looking at the loss function. And here on the left side, I'm showing you like a top view of the loss function. And on the right side, I'm showing you like a three-dimensional view of that very same loss function. And and so, oh yeah, so basically what you want to be is as close to the true parameter as possible. That's where the orange, that's where your solution should be, is around the orange true parameter. And the colors here represent your loss. So if you have a loss of 0, you're very close to your parameter space, to your true parameter. And if you in the yellows, you're very far away. And so also when I wanted to show you on the right side is, this is the loss function manifold, and it looks horrible. So there's clearly two big valleys, and in each of these valleys, there seems to be very like a large amount of potholes in that the solution that the other algorithms would get stuck into in the local minima problem. So the true parameter is located in this valley. You can see that, for instance, if you look at the solution for S1, so what we're trying to find is the orange solution. And you can fall within S1, for instance, if you fall in the local minima there, and you would have a terrible solution space, right? Sorry. And so these such local minimas are known to be problematic for numerical optimization algorithms. So this is why the system fails. You also have that in the S2, that's so if you remember the other valley, if I go backwards, well, let me go backwards. Basically S2 falls in this valley. And so even though the system would have found solutions for you, it would be not a good one. And S3 and S4 here shows you that even though there's a true solution in this space, the S3 and S4 solution are doing a pretty decent job at reproducing the orange trace. And so therefore, it would be nice to know right away if basically the variability around the optimal solution, to know where things are pointing. And so if we run the numerical solution of the Bayesian inference problem, it provides a density, a probability density spanned by two-dimensional parameter space. So the density is large, with a loss function as its major values. Okay, so we show the progress of the MCMC algorithm in the figures below. So as the number of collected samples increase from 2,000 to 4,000 to 8,000, and so as the sample count grows, the algorithm generates a long tail along the valley, showing a clearer picture of the parameter uncertainty. And I hope the colors are coming through for you. So the true parameter values are clearly visible in the high density region as a dark blue area around 250 picosiemens per micrometer for sodium and potassium conductances, respectively. So furthermore, the tail to the upper right of the true parameter shows the trade-off between sodium and potassium. So when the model output keeps being consistent with data, even though the values of the parameters deviate from the truth. So the point here, the takeaway is this algorithm is able to quickly fall into the valley that we're looking for and give you, if you look on the distributions on each side of the distributions, you can see distributions of the solution space. How am I doing on time? Kind of lost track.
you're about a minute. You have a minute more before we start the question and answer
Oh,
session. But if you need
okay.
another 2 or 3 minutes to wrap up, that's fine.
Okay. So basically we did this for 9 parameters. And so this is to show you, I'm gonna have to skip a bunch, but basically I wanted to show you that we can create these solution maps across many different parameters. And so if you look at the 1D marginals, so these are the marginals on the diagonal. So these are the specific parameters that you're looking for. These marginals, you can see things like multimodal solutions coming out, or you can see, for example, on the right for the potassium mediated calcium channel, the range seems to be cut off. So this method could also tell you that you're not looking along the right range. And then the other is the two-dimensional marginal. So basically showing you the different parameters with respect to each other. So there's some that have linear relationships, some of them are non-linear relationships, some are independent from each other, so it's vertical versus horizontal. And so I think I'm going to leave it at this. But the point is that, here, let me skip to this, the takeaway. So basically the model is agnostic. You can put any model in this algorithm. It provides you a landscape for the posterior distribution. And it's able to measure the uncertainty in one swoop. So that's my talk for now. Sorry, I went way over.
Oh, no, this is fine. You had 25 minutes and you took 26, so that's perfectly fine. So we have 9 minutes for questions. I'm just going to lead off with one question. How computationally intensive is this method in comparison to, say, gradient descent?
It's basically what's the problem that we have. So the problem that you have with this method is that you have to solve the ODEs over and over again. And so most desktop today, we did this on a 16-core desktop, and it was able to do it within 24 hours for a single cell. And so it also depends on the number of chains and iterations that you want to run, but it's not out of the scope of local machines that people.
Do you have any sense of how it would scale with numbers of parameters?
So yeah, every time, yeah, it's a good question. We're actually working on that, but there is a limit to which it's not linear. So I know that as you're increasing the number of equations, the time to solution increases non-linearly in a bad way.
Matt.
Yes.
Yeah, I just had a question of, this kind of maybe gets to your last point, and don't know the algorithms very well. But one of the things obviously that's interesting that you kind of got is, the redundancy of these things. So some parameters can be very important and very kind of well-defined. Other ones can be less defined. And then also some might have covariances where you can vary one, but the other one would compensate. I'm just wondering, does the algorithm, it seems like because it is kind of implicitly trying to give you the overall landscape of the parameters, is there something that comes up naturally that tells you that structure of that redundancy of where the trade-offs are, or how you can figure out those covariance patterns? Because that would be a really nice feature as well, if you could actually read those out kind of, I don't know if it's in the covariance of the posteriors or something like that.
I think, yeah, so it's in the, yes. So you should be able to calculate those, the covariance between 2 parameters and more. I mean, here I'm only showing 2 at a time because it's the way to visualize it, but you can pop those out.
But is it, I guess it's one thing to kind of make these plots and then you see these lines. I guess I'm just wondering if there's something that's a little bit more synthetic that can give it out without having to do another set of research questions to analyze your solutions. If there's something that kind of gave it to you in a more direct way. I'm not sure if that makes any sense, but.
So you're basically looking for like a covariance matrix for the 9 dimensions.
Maybe that's just what it boils down to. I'm not sure, but yeah.
Right.
Something along those lines.
No, that's an interesting question. I mean, intuitively, I think you could do it. How to do it, I have to think about it a little bit. But the point is that you do see these points. So you do see these landscapes, and these landscapes have values. So you could do a covariance on those loss values. If that makes any sense.
Generally, yeah. I think sounds good. Thanks.
Sure.
I see Badisha has a question.
Hi.
Hi.
So yeah, maybe my question has been already answered. So my question was like that, how much time your MCMC algorithm is taking to estimate best parameter for a given data set? This is
Yeah,
my,
so, okay,
yeah,
go ahead.
yeah, this is my first question.
Yeah.
And my next question may be very silly. So how many differential equations you have? One or more than one?
Could you
So
repeat the second one? Sorry, you cut.
yeah, yeah. So is there any differential equation in your model? It is Hodgkin-Huxley model, right?
Yes, it's a Hodgkin-Huxley model. Yes. And
So how many set of differential equation are there? One
so
or
no, it's
yeah,
so basically it depends on the channel, but
yeah,
I think we're around like 13 equations right now. 13 ODEs.
13 ODs
Yeah.
and a
And so
number of parameters.
it takes so it was 9 parameters, 13 ODEs, and it would take around 24 hours to run the chains.
Okay.
Because we ran I think up to like 40,000 iterations.
Okay. Okay. Yeah.
Yeah.
Thank you. Thank
Sure.
you. Yeah.
So I just want to go back for a moment. One of the things you did at the outset, which was very exciting, was you provided a sort of an overview of a panoply of different approaches that can be
Yes.
used. So that raises a question of whether it might make sense to do some kind of a hybrid. In other words, part of the issue is you're trying to get good priors. If you start from good priors, it looks to me like you might converge much faster and get to where you want to go, even in a higher dimensional space. Whereas if you're starting with no information, then you're very far away from the place. It may take many, many iterations to get close. Is that a fair thing to?
That's fair. That's
so
fair, yeah.
If you had ways of using some of these other techniques to get within the region, then if you're in the region, but you're not yet there, then maybe combining that with this approach might give you the best of both worlds. I just wonder if you thought about that.
So we're thinking about, so we call it a hot start. So we're thinking of doing basically building an AI model. So an artificial neural networks to give you a sense of where your parameter range should be. And that would basically calculate the priors using that artificial network and then running the MCMC. So that's like one way to do it. We call it hot start. There's also, I mean, hopefully this is where I look towards the experimentalists. So I work with CJ and Randy, and they have, it seems, these values like innate. they know where to look. And so so that's where the priors could come in. Like, basically human knowledge is very important. So that's another way of doing it. And the problem with the first one, like the computational methods, is the loss functions are so nasty, so full of holes that you're almost set to be, like, you're almost doomed to be stuck in a local minima. And so what I'm trying to get at is, if you get stuck in a local minima, is that could you build your range, basically your parameter range, knowing that?
That was, I mean, one of the things I was thinking about is that's where genetic algorithms are often very helpful, because they don't tend to get, they don't care about the landscape. They're not using gradient descent. They're just looking at the fitness. And because the patient can take you very far along the different parts of the surface, they often don't get stuck in local minima because of the way they're designed. So that was what I was thinking, is potentially combining something like a genetic algorithm, which is also somewhat distribution agnostic. It doesn't scale as well, but it might get you, as you say, to the hot start. And then using this, you might be able to get something that was computationally much more reasonable.
Right. But I still want to stress, like, this method was not out of the scope of your local machine. Like, if you buy a modern you know, within, I mean, the machine we use is 4 years old now.
Yeah, yeah.
So it's not inaccessible. You don't need to go to Argonne. We started at Argonne, but we quickly realized that we could do this at home.
Yeah, that's very, very helpful. I see we have a question from William Norris. William?
Hi, just a quick question. So you've shown this, your method here. So to at least my understanding from watching the presentation is that you end up with these kind of image maps comparing each parameter to like another. So like you have a bunch of maps of one parameter compared to another.
Yes.
Right. And so you end up with these trend lines showing how one parameter relates to another. But as you said, right, the Hodgkin-Huxley model has a bunch of different parameters that are all kind of interacting with each other. And ultimately you need to pick, you know, a set of parameters that drive the global function of the whole neural model.
Right.
So I guess
that's where I ran out of time. I'm sorry, I need to give another talk again. Sorry, guys. But basically what you're getting at is you see how there's color within these maps? So each of these represents a point. Okay, one solution, and the color represents the loss that you have.
Right.
So I was going to talk about this later. Sorry, here. Let me jump here because this is work we've been doing with Clay at Case Western and Roger. So basically, you see, this is a solution space for.
Let me interrupt for a moment. We actually cheated you of some time.
Yeah, so you can spend a little bit more time.
You actually have another 9 minutes of counting questions and everything.
Yeah,
okay.
Yeah, so you can go through this and don't feel bad about that.
Oh, I see. Okay. So here, this is basically, we're trying to solve a 12 degree of freedom problem, which is it's a CMM. It's the same network, but with a little bit more complex. And here you can see the black dot across that matrix. And so that's if Clayton was if I understand the data from Clayton correctly, that is the lowest value for each of these for that parameter set. So that black dot will move in space with respect to the range of the parameter sets. Do you see that?
Can you use your cursor? Use your cursor to show them.
Do you see my cursor at all? Points. Let's see. Do you see that? You see my cursor moving?
Yeah, now we can see it.
So this black dot here is the best solution of that map. And it moves, so, but it's not independent. So you can't pick, so if you look at the marginals here, at the one-dimensional marginals, you can't pick the best of all of them.
So
you have to pick what you think are the best value or what the most important value is for you. And then, and we usually pick it with respect to the cost, right? So if you actually want a solution that's interesting, like if you want an actual solution, you pick your cost value that has the lowest value. And that gives you, then you can back calculate the parameters from there.
Okay, yeah. So just to wrap it up with the intent of my original question was, you have all these feature maps relating the optimized landscape of one parameter to another.
Yeah.
Across this whole space. And right now it seems like you then get this representation where you have the relationships for each individual parameter, but it's still up to, you know, a user with some knowledge to then look at all these landscapes in conjunction and come up with which sets of parameters they think would fit best, or which sets of parameters to judge for the next round of testing. Do you foresee a way of automating that process in order to scale this to larger networks? Because if you have I just foresee if you have a network with a ton of Hodgkin-Huxley neurons,
Right.
you know, individual evaluation of this whole landscape is going to become harder. So do you see kind of a computational way forward of progressing to the next step?
It's a valid point. And what I would do, in like right off the cuff here, I would just start ranking your loss functions. And so, you know, so each of these points, each of these maps is an actual, there's an actual loss associated to it. And so you could start, you know, rank ordering all of them, and then you can start picking, you know, you can set a threshold at which you don't want to look at values any, you know, above a certain value, and then you can start exploring all those parameters. Does that make sense?
Yeah, that makes sense. Thank you very
For
much.
example, here, if you know, but I'm doing this with my eye, right? But here, like right here, there's a band that's a little more purple. So that has a higher level, you know, the algorithm shows this lowest, this black dot here as the lowest, right? But we could be exploring this space as well because it's got a low value. It's got low loss over here. And so the points associated with this would look completely different. Like if you were to pick a point in that space, the black dots would move respectively with respect to all the 12 dimensions. I hope that makes sense. We're looking to also put this online. So have a web or some sort of interface where you would click on an actual value and you would see how your points, how your parameter space would move.
Yeah, I mean, it seems it's very valuable because you're taking a high dimensional problem and you're scaling it down in a way because you're reducing the dimensionality to something that, you know, a person could interpret. It's still, you know, it's still a lot of dimensions, but there's, you know, it's good progress forward in my opinion.
Yeah, and we're hoping that, you know, people would use this as an experimental tool. So if you're able to, you know, some region might pop out like this one that you're not expecting, and you could go into your lab and test that region out. As you know,
gotcha. That makes sense in this context.
Yeah.
Are there any other questions for our presenter? Okay, well, I think this would be a good time for us to plan our break. We have until 20 minutes after the hour for the break. Roger, confirm, right?
Yes, that is correct. 20 minutes after the hour. We will see you in approximately 28 minutes.
Right, Matthew, thank you for an excellent presentation, and I look forward to seeing everyone at 20 minutes past the hour. All right?
Okay.
All right, take care, everyone.
Bye-bye.
Hey, Ken, did we record the break?
Sorry, what was that, Roger?
Did we record the break?
We did, yes.
Yeah, okay. Glad we have that.
Yeah, oh yeah. I might be able to post, I might be able to do some editing if
Yeah.
necessary.
We'll worry about that later.
Yeah.
All right, Roger, do you want to do the introduction? Or do you want me to?
Go ahead. It's your turn.
All right, that's fine.
I mean, it just takes too long to introduce Ansgar. He's way too accomplished.
I think Ansgar will want to spend more time with his talk than on the introduction, so I will be brief. So it's a privilege to introduce Ansgar Buškas. He has been a leading, the pioneer, I would say, in the analysis of locomotion in insects, with his work on stick insects initially, and now more recently on Drosophila. And at the same time, he has assumed an increasing and very important administrative task. Most recently, he was the vice rector for academic career and equal opportunities at his university in Cologne. And he has received multiple honors. I'll just mention that he's currently is a member of the Academy of Sciences and Arts of the province of North Rhine-Westphalia. And he gives really outstanding, lovely talks. So it's really a privilege to have him with us, and we look forward to hearing what he has to say. Ansgar.
Yes. So, thank you very much. First of all, you can see my screen. Hello?
Not yet.
I was too fast.
Now
you can see.
Yes, now we can see the screen, but it looks like your screensaver, not your talk. Now we see your talk.
Okay, so first of all, thank you very much, Hillel and Roger, for inviting me to contribute to this lovely symposium. And we move very much into biology with my presentation. And I, within the next 25 minutes, would like to give you some insight in our past and recent work on task specificity in the control of insect walking. And let me first switch to laser pointer. Here we go. So essentially, what do I mean by task specificity? Well, actually, what we know a lot about, and this will come again in a brief summary on the next slide, is straight walking in insects. And well, but they do much more. They can do backward walking, as you see here. They have to cope with terrain where they lose ground contact and have to search for new foothold. And finally, insects have to navigate through their environment also by generating specific locomotor behaviors like curve walking. So what do we know about at present about also what's the starting point of what I want to go through with you today? And actually, we know quite a bit about what one could call the default generating motor activity of leg stepping in forward walking. So in the stick insect, it has been analyzed in quite some detail that we do have a modular organization with individual CPGs generating alternating activity in the main leg joints. And secondly, we know that sensory feedback from force, load, movement, and ground contact sensors contribute to coordinating the CPG motor activity for leg stepping. And that allowed us in the past to generate, here we go. It's a bit slow in the presentation. We will get there. Yeah, here we go. Yeah, here we go. To generate simulations, dynamic simulations, as well as kinematic ones, where we could essentially check out whether the mostly in restraint preparations collected influences of sense organs on the activity of those joint CPGs can account sufficiently for the generation of specific stepping patterns of the stick insect leg. And essentially, to cut this scheme, which is quite awful and detailed, short, means that we need to focus on these 4 phases that I deliberately divided the step cycle in, which is the start of swing phase, the stance to swing transition, the swing phase, the swing to stance, and the stance phase. And when you cut the story short, we know today that movement and load feedback, and that, by the way, accounts also for mammals and walking vertebrates, is important in controlling stance to swing transition. Swing is mostly controlled or generated by the contribution of movement feedback. The swing to stance transition is generated by the contribution of movement load and ground contact feedback. And finally, during stance, we have movement and load feedback. So essentially, having said that, that's the regular. But the challenge is what we would like to understand is, and this is coined by the term task specific, actually is how does the stick insect, and this one is not starting to move, I'm sorry. Here we go. Now it's starting to move. How the stick insect does generate stepping cycles with each individual leg by having, for example, obstacles to surpass. By the way, this is the same holds for, in the way of not knowing how it works, for vertebrates, for example, in climbing or dealing with unpredictable terrain. So when it comes to the generation of task specificity, we have looked in large insects on the mechanisms that are in charge of contributing to forward versus backward walking, or straight versus curved walking, or changing walking speed. In the past years, because of the advent of the possibility to use neurogenetic tools for doing causal analysis on the circuits that actually generate walking in insects, we have started also to use the fruit fly. And today I'll give some information on changing walking speed and backward walking in the fruit fly. And when you do so, and this has been so nicely alluded to by Gregory Sutton in his talk, you have also to to answer the question, how does the fruit fly walking system compare to other walking systems, also larger insects? For example, the control of interleg coordination when changing walking speed, or in more general, the organization of the fruit fly walking system. In Neuronex, we are eager to follow up on the work that we now have started on curve walking. So I will talk about 3 aspects: changing walking speed, intersegmental central coupling, and I will present first results on individual premotor neurons controlling step phases. So changing walking speed, where there is a long-standing dogma, and that also goes back to a question that Gregory Sutton had, which is the size of an animal actually determining the gait or the coordination that you see between legs? And actually, there's very little known also for insects, but what is known is that you find in slow walking insects or under loaded conditions or in unpredictable environment, you find the tetrapod coordination, which is shown here with the black bars indicating the swing phases and the white open spaces, the stance phases, and easy to see that you have 4 legs always on the ground. When you have fast locomoting animals like for escape or in fast walking or with predictable environment, you find what's called tripod with 3 legs in the air at any given time and having 2 tripods sort of alternating between each other. And the common notion is that you have a strong peripheral control in slow walking and a strong central control in fast walking. We can discuss this potentially later on because there's new evidence from other invertebrate species that sheds some light on that idea. So when we started to work on the fruit fly, we wanted to know, is it so that the fruit fly, as was reported in the literature, does generate tripod coordination and only merely or very rarely tetrapod coordination? Or what does the life cycle or the life, let's say, behaviors, the locomotor behaviors of the fruit fly offer to the researcher? And guess what we found? The fruit flies do generate all 3 different coordination patterns. The wave gait, which is with 1 leg in the air at any given time. When they walk faster, this coordination pattern changes to tetrapod and finally to tripod. So obviously, Drosophila changes interleg coordination depending on the speed of locomotion. And there's one thing which I think is important to keep in mind. This is that even if Drosophila often walks tripod, it doesn't mean that their nervous system is actually tuned to do that. The thing is that the environmental requirements, if they ask for other coordination patterns than fast locomotion, it's important to know whether they can do slow or very slow locomotion, okay? So what we wanted to know is there something like a tripod gait used by fruit flies during walking? And this is work mostly done by Anne Wosnitzer together with Till Bockemühl in my lab. And what we did was actually very simple. We checked for the quality of the tripod. And what you do to do so is you look at the 3 legs of one tripod and you take the first leg starting of the swing phase or stance phase and the last leg ending it, and you take the joint activity of this phase and you essentially do the quote of this. And what this means is that you get something like a tripod coordination strength index, which can vary from 0.8 to 0.1, which means in 10% of the time, 3 legs are doing the same thing, and in 80% they are doing the same thing. Now the question, is tripod a gait or not? Well, I would say no, and actually the literature has accepted that quite ubiquitously, because when you look at different strains of the fruit fly, that wild type strains, you see that the tripod coordination strength changes as a function of speed, starting at very low levels when they walk slow and going up to 0.8, 0.9, never hitting 1.0, which is actually a result of the phase lag between the leg pairs of and walking insect. So what's the conclusion? The conclusion is that tripod coordination strength in fruit fly walking changes as a function of speed of locomotion, indicating that there are no gaits in fruit fly walking. And it's important to keep in mind that when you look at quadruped walking and their gaits, that they are specifically defined by their coordination patterns, and that you can only go from one gait to the other by specific intermittent steps of a single leg in order to qualify for the new coordination. In insects, when they speed up, they simply need to shorten the stance phases of all legs, and that will do the job. So the next question is then, is the leg muscle control system of the fruit fly organized in a modular fashion, as for example, supposed by data on stick insects and other insects? So this will be the next part of my talk on intersegmental coupling. What did we do to study the organization of the walking control networks in the fruit fly? Actually, we went back to a 70s approach with a model animal which is neurogenetically approachable, which might take you wonder, but there's a beauty of this approach, because when you remove the distal segments of a leg, and this is shown here for a slow walking fruit fly and for a fast walking fruit fly, and that has been known for long for various species of insects, the leg stump shows oscillations. And it's easy to see that these oscillations in the slow walking fruit fly appear to be faster as compared to the stepping legs, while this big difference is at least not detectable when the fruit fly walks fast, okay? It looks pretty orderly or coordinated, but you can nicely evaluate this. And when you do so, and we first focus on the oscillations of the legs and the stump, which is now here a middle leg amputee, you see that there's no difference in the number of oscillations over time compared to the front leg and hind leg with a fairly fast walking fruit fly. What happens when the fruit fly walks slower? Well, the stepping legs slow down quite a bit and cycle period becomes longer. However, the cycle period of the stump, well, it becomes a bit irregular, but it's much faster. So let's quantify this. This is showing for the front leg, the middle leg, and the hind leg, the cycle period of leg stepping as a function of speed in body lengths per second. And sure enough, in an intact animal, the cycle period decreases as a function of speed. What happens for the amputated middle leg? And this is interesting because you get a constant cycle period. The same is true for the front leg. And the same is true for the hind leg, which let us come up to the conclusion that independent cycle period of leg stumps suggests only weak intersegmental coupling and segmental modularity of CPG networks for rhythmic locomotor activity. This is also nicely shown when you compare the average cycle periods of the front and the hind leg with the middle leg stump at different speed ranges, and you immediately see that this cycle period stays the same. Well, the question is what happens to the phase of oscillation with respect to the neighboring legs? And this is shown here for the phase of oscillation of a middle leg stump with respect to front leg. And this can be shown quantitatively that the variability in the phase distribution becomes smaller, the faster this fruit fly walks, which is shown here by a front leg stump in relation to the hind leg, okay? So conclusion, the fruit fly walking system controls interleg coordination comparable to many other insects. The neural control of fruit fly walking shows segmental modularity. So obviously there's evidence for weak intersegmental neural coupling in fruit fly walking. How about individual premotor interneurons controlling step phases? Well, when I showed you this scheme, immediately for a neurobiologist, the question arises, who's doing the job? Which neuron, or can we identify individual neurons that are either elements of those CPG networks, or to take the question a bit on the simpler and more phenomenological level, can we find individual neurons that contribute to the different phases of stepping off a leg? Here, a fruit fly leg. But the fruit fly poses a very tremendous problem to a researcher when he wants or she wants to study walking, because fruit flies have the habit to walk continuously forward, which is pretty bad if you want to start walking because they already do it. So we needed an experimental paradigm which allows for studying leg stepping in a controllable fashion. And it was the PhD thesis of Salil Bidaye in the lab of Barry Dixon who actually created the solution by finding two pairs of descending neurons, the MDNs, that upon activation, they induce backward walking. And you see this here on a movie. This is MDN modified genetically by introduction of an optical sensitive cation channel. And when the light goes on and the laser goes on, then MDNs are activated. So now this is spontaneous forward walking. And now you see what happens. As soon as the laser goes on and the MDNs are activated, everybody will agree that this fruit fly walks backward. Actually, there's an impressive set of experiments that has been published by Salil in this science paper. When you give them these animals the activating light all day, they will never walk forward again. So MDN activation induces backward walking. Now we have a chance because as we can induce backward stepping, we can now pose the questions to which neurons does this neuron connect? And to go to the last slide again, this is a brain neuron sending his axon collaterals to the ventral nerve cord, where the networks reside which are controlling the individual legs. So first, by using TransTango to identify postsynaptic partners, and then to add to those postsynaptic cell types specific calcium-sensitive dye, made it able that Kai Feng, Ryo Minigishi, and together with Rai were able to use calcium imaging to identify postsynaptic partners of the MDN. And this picture is not to be explained to you. It just should show you how many of those neurons that were identified actually react to the activation of MDN by an increased calcium influx, which is can be interpreted as synaptic connection. So this one, MF09, had a very strong calcium signal in the metathorax, which is the leading leg in backward walking. So what Kai Feng did, he created lines where he had tagged MDN and this later on called local interneuron 128 together. And here you see MDN, the arborizations in the VNC. You see the local interneuron 128, which shows serial homologous partners in all three VNC segments. And here you nicely see a fluorescence image of the pairwise occurring LEN 128 on either side of the metathorax. So then what he did was that we again optogenetically activated this neuron LIN 128 in a resting animal. To make a fruit fly rest, you have to remove the brain, which means that this fruit fly, you only activate 128, and you see in the standing fruit fly, always when the laser goes on, the leg is lifted. The story becomes more interesting when you now combine the MDN activation for backward walking with LIN inactivation. So here you see that the fruit fly is starting. The movie is a bit ragged. This is too bad. Perhaps I start the slide for a new time. Sometimes it goes nicer if you do it the second time. Wait a minute. Here we go. Perhaps. Yeah, you see the quantitative data in a second. So what you should see is that when LM2022 is silenced, that induces an outage of leg swing. And I show this with the quantitative data much more impressively. On the top data set, you see that backward stepping is starting with MDN activation, which is depicted by the red bar. And you see that the hind leg is walking, stepping backwards with all the different joint angles that we can measure. When we then inactivate LM2022, you see that the stance phase is prolonged and prolonged and prolonged. And in many cases, it will only resume after you stop inactivation for LM2022. So LM2022 leads to abolishing or delayed stance to swing transition in backward stepping, which means that that single neuron is sufficient to interfere when you silence it, to interfere with the sequence of stepping motor activity for backward stepping. We also identified another local interneuron, which is called LM156. When you silence this one, you can stop the stance phase in the ongoing phase, which means you slow it down and slow it down and slow it down, which means that this neuron is serving stance in backward stepping, which means that individual interneurons serve the generation of specific phases of the leg stepping cycle for backwind stepping of the fruit fly. And this brings me to my final slide, that we are at the moment able, with respect to task specificity in the control of insect walking, to describe and address specific individual premotor interneurons that control phases of leg stepping in the backward stepping fruit fly. Having said that, I want to thank my contributing lab members. The ones in green are the ones which are involved in Neuronext: Till Bockemühl, Michael Dübbert, Axel Gorostitzer, Ricardo Custodio, and Gesa Dinges, who has left the lab, but you will hear more about that potentially or most likely in a second or two. And apart from other funding and very interesting collaborations, we are honored and happy to have the support of Neuronext for doing this terrific collaborative research together with our colleagues in the UK and the US. And with that, I thank you very much for your attention.
Thank you very much, Ansgar. Okay, we have time for some questions. Yeah, Nick, why don't you go ahead?
Sure. Ansgar, thank you for the talk. It's always great to hear these things straight from the source, right? So, you know, for example, you shared the data from the Berendes paper. It's a classic, showing that when some of the sensory feedback was removed from the stump leg oscillated much more quickly than the other walking legs, unless the animal was walking very fast already. Correct?
Yeah.
And, you know, again, correct me if I'm wrong, but based on the things that I've read, I feel like there's kind of this feeling in neuroethology that typically deafferented pattern generating networks oscillate at a lower frequency than what's observed in behavior.
Yeah.
And so I guess, you know, it's something I've thought a fair amount about. Do you have any specific hypotheses about how sensory feedback may be utilized differently in these different systems, or how maybe these are all separate parts of one complicated self-consistent tapestry? Yeah.
Thanks for the question. And actually, I jumped these two sentences in the talk because the leg stump cannot be considered as, or the segment with the leg stump cannot be considered as deafferented, because we only have essentially removed the opportunity of the leg stump to generate a stance, which means that movement sensors in the thorax coxa joint and the coxa trochanteral joint and the trochanterofemur joint, which is, by the way, specific for the fruit fly, are still present. This is important, number one, which means that the higher cycle period can come from local influences, and as well, we have all the intersegmental information flow present in that condition, okay? So that's number two. And number three, actually going back 30 years, it has been shown that in the locust flight system, that sensory feedback actually serves not only the sculpturing of the flight pattern by switching between elevation and depression of the wing, but shown for this with a beautiful paper by Ramirez and Pearson, I think it was in 1989 or so, that essentially the stretch receptor puts up a background excitation that is already sufficient to influence the activity of the flight CPG. And therefore, I would not claim, number one, that we have CPG activity here. Number two, those mechanisms are well suited to account for the observed higher cycle period than the slow walking Drosophila.
Yeah, no, thank you. You're certainly right. There's removing one portion of the leg is not the same as de-efferting. So I appreciate you clarifying that. Thank you.
Ansgar, I just wanted to quickly ask, you spent a great deal of time working on the stick insect, and now you come to Drosophila, and you argue that basically Drosophila does just modified tripod gait, whereas the stick insect showed a whole range of different gaits. So would you say that, is it possible that the scale issues that Greg raised might account for this, that you don't need any other kinds of gaits if you're a Drosophila for the kinds of things that Drosophila does? I know the stick insect has to live among leaves and it has to move very slowly and it has to be, so what are your thoughts on that?
Thanks, Hilal. Perhaps it slipped the attention that the one slide that I showed on the different coordinations patterns, they were all collected on the fruit fly. The thing was that as compared to the initial work by Strauss and Heisenberg from 1990, where they took what the fruit fly does all day long, which is mostly tripod, actually, Anne Wosnitzer didn't like me when I asked her, please look also at slow walking fruit flies. And actually, she hated me, if one may say so, in lab jargon, because fruit flies, you have to catch them when walking slow. Why is that important? It's only important because it has been this notion of hidden dogma that essentially when you have a system working fine at high speed, you simply tune it down and it will be all good with tripod when it comes slow. That's not the case for the fruit fly. However, what the fruit fly shows with this experiment that Nick had just alluded to with the single stump, the change in the phase of variability of phase shows that there is a change in the coupling between the legs, and that it's highly likely that the system is tuned across the speed range for changing the gain of central coupling. But that's a wild hypothesis that I'm just bringing up here.
Very nice. Thank you. Thank you. We have time for a few more questions for our presenter.
Yeah, I can ask a very ignorant question. It's kind of coming from the vertebrate side of things. Because I always think about, people talk about kind of the development of locomotion in vertebrates and say you have this kind of primordial sinusoid to the backbone. And then you kind of add on the legs, but it's kind of, you add them on to that kind of sinusoid, right? And so and my understanding is that, I'd like the work of people like Alain, Frignon, and others to kind of have emphasized the coupling between segments to kind of, that could make that happen. I mean, there's both peripheral and central, but I was thinking the central as being very important and kind of that traveling wave to find that. Is that a difference between vertebrates to invertebrates? Or do you think it's a similar kinds of things that I just don't know what I'm talking about?
Actually, we already talked about a creature which is dynamite to look at that question. And this is the crustaceans, because the crustaceans have the walking legs and they show some, let's put it this way, an interesting variability in coordination patterns when walking. However, the uropods, which are the homolog appendages of the abdomen, which carry the gills, they have exactly what you alluded to, like in the spinal cord of vertebrates. They have a very firm segment-to-segment central coupling, which essentially allows for a wave of the gill leg carrying uropods in the establishing this sort of breathing pattern, if you would like. So I would say the reason for the difference is not the legs. It is that you have the specializations of the legs, which make the system more open for peripheral feedback. However, when you don't need ground contact, like for example in the Europods, then you go back to a very nice organization of intersegmental networks coupled quite strongly to each other.
Cool. Thank you.
I see Roger has a question.
This goes along with some of the other questions. Fruit fly versus stick insect, considering Greg's talk, do you see any difference yet? I mean, do you see any difference in neuromechanics, based on the difference of scale?
I think that the next talk by Gesa and its consequences to look at load and force feedback in the control of leg stepping and intersegmental coordination will actually allow us to get insight into whether we can assume neuromechanical coupling in a light and small animal like the fruit fly, which is operating in this viscous dominated regime, as we heard by Greg, as compared to the stick insect in the quasi-static regime. At the moment, I would say they are similar enough for us to do research on both, on questions which are complementary to each other, and where we find the better approachable experimental animal in the one or the other.
There's a question from Michael Benning.
Yeah, go for it, Michael. Michael, you could speak it aloud, Michael.
Hi, Dr. Buschkes. Early in your talk, you mentioned central control and peripheral control. Do these tend to relate to feed forward and feedback control respectively, or is this more related to the modularity you talked about? No, actually, central and peripheral control, in principle, would allude to what you said, what you suggest, feed forward and feedback. The question of modularity is a question which is then coming down towards the entities of subcircuits and sub-networks that you have, which are coupled to each other. But that these feed-forward feedback account for each of those sub-networks in a similar fashion. Does this answer your question? Or did I confuse more than explain?
I see. Great. Thank you. Michael, you could talk, you know.
I'm in the office suite and it tends to get kind of noisy in here at times. I didn't want to bombard with peripheral noise. But yes, thank you very much. That was exactly the question.
I suppose I have one more brief question if we still have a couple minutes, or unless we'd rather move on to the next talk.
No, we have 2 minutes, so please, by all means.
Okay. Yeah. So Ansgar, I really liked seeing the local interneuron 128 and others. Has anyone looked, or are people looking at what parallel, I don't know, structure or processing there might be between these interneurons and the fruit fly and these other classically archived interneurons in stick insect or locust thoracic ganglia, or is it right now we're just seeing what sticks to the wall?
Well, actually, when we started out, when Barry Dixon and me and the collaborators, the visiting scientist project that I had at Janelia, the idea was actually, we did a big survey of known local interneurons in cricket, in locust, in cockroach, in stick insect, in order to find an easy way to compare them by their morphology and potentially later on their function with each other. The thing is that there's very impressive work, highly interesting and relevant work by John Tuthill. He has looked at the processing of specific sense organs, and by that he found the first neurons that he said could be. But to get back to your question, this comparison was not easy enough based on the morphology. Therefore, we did not go further here. So we need much more information about postsynaptic partners and physiology during, for example, locomotion or at rest or processing which kind of sensory feedback.
Yeah, great. Thanks. I appreciate it.
All right, I think we're at time for the next and final presentation. And Roger, I'll turn it over to you.
Okay, it is my great pleasure to introduce Dr. Gesa Dingus. As Ansgar just told you, she worked with Ansgar at the Institute of Zoology at the University of Cologne. There, she worked to characterize Drosophila leg companiform sensilla, which are strain centers, and the role in intraleg and interleg coordination. Gesa is now a postdoc at West Virginia University with Nick Shishensky. Please take it away, Gesa.
Thank you. Let me share my screen. Do you all see my screen?
Yes.
Cool. All right. Okay. Well, thank you very much for sticking around for my talk. I will be talking about strain sensors in the leg of Drosophila, or the legs of Drosophila in various methods that we applied and the results that we got through them. All right, so movements are dynamic and require context-dependent adaptations. Different behaviors, like adjusting posture, as we see here in the first video, overcoming rugged terrain or gaps, as we see in the second video, or seemingly simple straight walking, as we see here in the third video, are examples of behaviors where proprioceptive information on the limb's relative position is used to coordinate efficient output. Proprioceptive sense organs are a key component of the neuromuscular system, in which, for example, interneurons in the VNC can drive motor neuron activity. These motor neurons can activate muscles, which ultimately leads to the activation of limb segments. So, for example, a flexive or an extensive movement. And these movements are monitored by sense organs, which can in turn feed back this information onto various entities within the neuromuscular system, ultimately leading to the modification or reinforcement of the motor output. Drosophila, as you probably all know, has 6 legs, 2 prothoracic legs, 2 mesothoracic legs, and 2 metathoracic legs. And each one of these legs is segmented into 5 sections. So we have the coxa, trochanter, femur, tibia, and tarsus. And the tarsus itself can also be subdivided into 5 sections. Within each of these sections, we can find both internal and external sensory organs, as this green GFP labeling here is depicting. Some of these sensory organs include bristles, which are these kind of like hair-like structures that can signal touch. Bristles can be grouped into hair plates in order to measure joint angle changes. There are chordotonal organs, which measure the relative position and movement of body segments. And finally, there are campaniform sensilla, or I will continue referring to them as CS, that measure strain that spreads throughout the cuticle. If we look at the morphology of CS in a little bit more detail, they commonly have 4 cell bodies, one of which is a bipolar sensory neuron that has a modified dendrite that reaches up just below this cuticular cap, which is embedded within the cuticle itself. This dome cap shape-like structure can be surrounded by a ring-like structure called the collar, and below the cuticle is another ring-like structure called the socket. So it basically loops like this, and this does as well. This dome cap shaped like structure is actually a key component of the mechanotransduction mechanism, because when compressive strains come along, this cap bulges upwards, which ultimately leads to a action potential in the underneath lying sensory structure. So back in the day, we wanted to start a holistic analysis of CS in the fruit fly leg. And we kind of focused on 4 main topics. So the outer morphology, the biomechanics, the neuronal morphology, and as well as the behavior. And we're going to start off with the outer morphology. For this, we use scanning electron microscopy to characterize all CS on the fruit fly body. And with this, we saw some interesting inter-individual and inter-leg differences. So first off, there are 680 CS in 26 fields, 54 groups, and 34 single locations on the body of the fruit fly. They are on the wings, halteres, on 1 location on the thorax, and in the legs. And they come in many shapes and sizes, as this summary picture kind of depicts. And we have everything from round without a collar, round with a very dominant collar, these very specialized CS shapes on the halteres. We have elliptical with a collar, elliptical without a collar, and so on. In the leg, we have 42 CS on average. They can be found in 2 fields, 6 groups, and 2 single locations. And also on the leg, there comes various shapes and sizes as well as orientations. As these yellow boxes mark, these are leg CS. And as you can see, there's quite the diversity in the exact shape of these sensors. And this is actually really essential for their function because these properties specify which strains these CS will encode. Because the arrangement and the morphology of the sensors actually makes them sensitive to specific strains. So elliptical CS are said to be directionally sensitive because they will compress along their short axis. So this elliptical CS will be sensitive to different strains than this elliptical CS if they're aligned like this on the, for example, long axis of the tibia. Elliptical CS can also be on a 45-degree angle to the long axis of their limb segment, making them sensitive towards torques. Circular CS are deemed to be more omnidirectionally sensitive. However, if they have a collar, they can be asymmetrically placed within the collar, making them also directionally sensitive. Grouping various CS is also beneficial for the system because it can encode the rate of force, because more CS will be recruited, the stronger the strain becomes. In some cases, we also find, for example, fields where various types of morphologies are in one location, which allows the system to encode dynamic strains in a highly specific manner. So some of the interleg variability that we found was if actually in just 2 locations, it's the single femoral CS and the single first tarsal CS. In the front leg, it's on the posterior side of this ridge, while in the middle and the hind leg, it's on the anterior side of the ridge, and the middle leg, it's even closer to the trochanter, and in the hind leg, it's a little further away. And this may be due to the actual morphology of the legs, because the front leg has a really predominant coxa, while, for example, the hind leg is a lot larger than the other 2, or relatively larger, not a lot. Right, so this might be that these different leg morphologies actually just produce different strain portfolios, but it could also be that the function of the legs during movement are different. So the front leg, does more of like a pulling movement during walking, while the hind leg pushes, and the front leg's also more involved in grooming and so on. Another type of variability that we found is the intra-individual variability. So this is the trochantral field, which can be subdivided into 2 subgroups. And if we just focus on the smaller field right here, and look at it in these 8 individuals, we can see that the location itself is very robust, but the relative arrangement of the sensors within the location is variable. So we have this case where there's, for example, like this crescent of 4 CS with 1 adjacent CS, while this one had 4 CS in basically the mirrored crescent orientation. This one had 5 sensors aligned in 1 row, and so on. We, of course, don't really know why this is the case or if it's even relevant. It could be that they're equaling out particular differences, or it could also be that these small scale differences in strain sensing are just kind of irrelevant for the system. All right, so the conclusions for the outer morphology part is that the CS locations themselves, especially on the legs, are very robust. However, the exact or relative arrangement of the sensors within it is variable and depends on the individual. Some CS locations are leg type specific, and the only location on the leg that contains different types of morphologies within one location is the femoral field, which we can see right here. And because this is the only location that has these very different morphologies and orientations, we're quite interested in investigating this further on a biomechanical level to see how these sensors that at one location are going to react to the same strain application. So we took the femoral field and went on to our next endeavor, which was the biomechanics. And for this, we used high resolution imaging and a finite element analysis to basically investigate the dynamics. So first off, we did a micro CT from the leg, and this is the femur right here in after segmentation. In purple, we see the muscles, and this orange spot right here are the cell bodies from the femoral field. We then used nano CT to image the section in more detail, and this is basically what one slice of the scan would look like. And after a lot of tedious segmentation, we got this, which is basically the segmented version of the nano CT. And here we can see all 11 caps. And we have 3 circular CS that actually have a collar, and the rest are elliptical without collars. And one of the interesting findings that we found just through the segmentation is that the sockets, so basically, if we look from the inside of the leg out, these things are actually interconnected in units. So these 4 are interconnected, which corresponds to these 4 caps. These 4 are interconnected in 1 unit, and it corresponds to these 4 caps. 7, 3, and 2 were not connected. What we did then is basically apply a tensile strain of 35 micronewtons along the complete distal end of the model. And we based this force on measurements that were taken during flight takeoff, where the maximum force was 70 micronewtons for both legs. And this is scaled 100-fold. And then we did various analyses, including a principal component analysis, to basically see how the orientation of the cap was in regards to the socket unit orientation. And we also looked at the displacement vectors for each cap, depending on this orientation. I'm not going to go into this in more detail, but our main, and we also altered the material properties of the socket and the collars to kind of see what kind of effect that has. And the conclusions from this work are that the material properties affect the displacement, the interconnected sockets affect the displacement of their respective unit, so the caps that are within that unit of interconnected sockets, and the collars, even though they're just around 3 CS, amplify strain of uncollared CS in that local area as well. And we believe these results are quite important for future investigations, because not only does the morphology vary between just within the leg, but the material properties do as well. And there's a lot of difference between different species in this regard as well as also. All right, so then to connect the knowledge that we gained on the morphology and the biomechanics of function, we identified CS cell bodies in the legs and characterized sparse driver lines. So after extensive literature and screening experiments, we ended up with 11 split-4 lines that mainly label CS within the femoral and trochanteral field, so this area up here. A couple of these also label CS in other locations on the leg, but it's very sparse driver lines, labeling everything between 1 and, let's say, 13 CS. And these lines were sufficient for us to actually check out CS function during movement. So that was then the next step. So with these lines, we could use the genetic tools that Drosophila provides in order to manipulate neurons in intact animals during walking and standing. So first off, the main leg joints that we looked at is the thorax coxa, coxa trochanter, femur tibia, and tibia tarsus joints. And these joints, of course, are under the control of specific muscle groups. So we have the retractor protractor controlling thorax coxa, levator depressor controlling coxa trochanter, extensor flexor controlling femur tibia, and long tendon muscles 1 and 2 for the tibia tarsus. And by alternating the muscular activities of these aforementioned muscles, the legs can cycle through their swing and stance phase and essentially propel the body forward. And these movements are resisted by the ground and are accompanied with increases and decreases in body load, which ultimately produces strain that spreads throughout the body. And the CS can monitor these strains and feed back on them to modify or reinforce muscular activities. And like Ansgar mentioned, there's been a lot of work in stick insects on the CS function. And to kind of summarize the effect of the trochanteral and femoral field, if we look at the swing and stance transitions and start at the late swing, while the leg is basically transitioning to the early stance phase, we have tarsal contact, and the femoral field can assist in the transition between the levator and depressor muscle. Then when the leg is going through the early stance phase and entering the late stance phase, we have an increase in load because there's more body weight on that individual leg. And this can be monitored, and the transition between protractor and retractor and depressor and flexor muscle can be monitored and assisted by the trochanter and femoral field. Then when the leg is ready to re-enter the swing phase, there's a decrease in load, and this can also be monitored or assisted by the femoral field in the transition between depressor and levator muscle. So the cool thing about Drosophila is that we can see how individual CS or very specific groups of CS actually function during this kind of freely moving, or if an animal is moving freely and is exposed to cyclic strains. And for this, we could use the lines that I described previously in a setup that we love to use, which is this free walking arena. For this, we basically have an arena where there's like a little Petri dish here so the fly can't walk away. And we have a surface mirror below, and we can capture it with a high-speed camera. And the fly is expressing green light sensitive inhibitory channel rhodopsin GTA01. So when there's green light, the cells expressing the GTA01 are basically inhibited. So first we let the fly walk through there in the dark, and this is captured, so it's our control. And then the green light is turned on, the fly walks through there again, and that's our inhibited state. So then we basically have a video like this, which is our control, where all CS are intact. And then we have a video like this, where the CS are inhibited. And then we can use deep lab cut to track the tarsal tips and extract kinematic and temporal data from this. So we can extract various information from this data. So for example, if we want to look at the AEP, so the anterior extreme position, the PEP, the posterior extreme position, which this is AEP, this is PP, for the front, middle, and hind leg. For the inhibited, so the filled symbols and the empty symbols are the control. We can compare this between different lines. This line inhibits these white marked CS, this one, these ones, and so on. And if we just look at if the PEP or AEP shift during inhibition, we can, for example, see in these three lines that the meso and the metathoracic legs seem to kind of have a shift, a posterior shift in the placement of their APP and PEP during inhibition, while the front leg in all three of these lines doesn't really show that. This is, of course, very preliminary data, and we haven't really figured out what this means, but it's definitely interesting to see that the inhibition doesn't not necessarily affect all three legs in the same manner. Something else that we like to look at is the interleg coordination. So basically the relationship of one leg to another. For this, we take a step cycle from one leg, for example, the left hind leg. So from one PEP to the next PEP, and check out where the PEP from a corresponding leg falls within this normalized cycle. And this is just an example of some of this data. So blue is the inhibited state it's in a slower walking data set, and this is from the same fly. And this is in a faster walking data set from the same fly. And we can see that the inhibition during slower walking seems to create greater variability in the placement of the corresponding leg. So a plus value would be a later PEP, and a minus value an earlier PEP in the normalized step cycle. In faster walking, we see that the variability isn't increased as much during inhibition, which is something that we saw consistently throughout the entire lines that we screened. Another thing that we like to look at is the intra-leg coordination. For example, for this line now that labels VCS, so VCS are inhibited during the inhibition. We look at things like swing duration, so how long is the leg in the air, stance duration, how long is the leg on the ground, stance amplitude, so the distance between a PEP and a subsequent AEP, and stance linearity, so how straight the stance phase actually is. And we have this for the front, middle, and hind leg. And if we look at this data for this one fly here, we can see that, for example, the stance duration shows a greater effect in the front leg than in the middle and the hind leg. Whereas, for example, the stance linearity doesn't really affect any of the legs. Right, so to kind of visualize the data a little better, I have this crude depiction of the lines that we tested in increasing order of how many CS they label, and the bottom four also label CS outside of the femoral and trochanteral field. And this is the swing duration, and this is stance duration for the front, middle, and hind leg. And these arrows basically show if the median values of the inhibited state lie outside of the quartile boxes from the control. So if you just look at this, we can see basically everything. We see increases, decreases. We see the same effect for all three legs. We see somewhere here, we also see different, for example, here we only see increases in the middle and hind leg. Here we only see that one leg was affected and so on. And this is for a slower walking group, and in a faster walking group, we also basically see the same thing. There's no like consistent trend of what happens when these CS are inhibited for each leg or each walking speed. So as a conclusion, the inhibition of CS subsets affects intra and interleg coordination. There are different effects on the intra and intraleg coordination at different speeds, and the inhibition affects different legs to different degrees. So something that we always also wanted to look at, just because we had the lines finally, was to see what actually happens if we would activate the CS. And for this, we use Crimson, which is a red-shifted cation permeable channel rhodopsin. And these flies that were expressing this were basically tethered, and I used this optical fiber to activate CS while I was capturing from the side. And then we used deep lab cut to track joint angle changes in the hind and front leg. And so this is an example line that is labeling these CS. And when I press play, we'll see a little white box up here that basically signals when the CS are being activated. So if we then quantified that, we could see significant joint angle changes in the thorax coxa and tibia tarsus joints in the hind leg, and the coxa trochanter, femur tibia, and tibia tarsus joints in the front leg. And the direction of change could be correlated with protractor, levator, and extensor muscle activity, which are muscles necessary for the swing phase. Of course, we can't say, okay, CS activation leads to activation of these muscles. These effects could also be because an antagonist is turned off and the agonist is turned on. There's a co-contraction that's kind of uneven. It could also be that it's actually muscular activity induced by this, but we have no idea why this is actually an effect, but it's cool to see that we see something. Yeah. All right. So again, I plotted the lines in increasing order again. The bottom two have CS outside of the femoral and trochanteral field. This is the suspended data, and this is the standing data. So in the one case, the fly is standing on a ball, and the other one has no ground contact. Hind leg, front leg, and the 4 joints that we looked at. And the stars just represent if there's a significant change in joint angle. And by first glance, you'll already see that the top half of this is quite empty, which kind of implies that, the more CS are activated, the greater the effects we see, or the more effects we see, which is not the case during the inhibition. During the inhibition, we also had plenty of changes in this line, for example, that only labels 1 CS. What we also see is that the suspended state has more significant changes than the standing state, which could be due, for example, to mechanical coupling. And we also see that they're not necessarily the same changes in the front and the hind leg throughout this data set. And finally, we can also see that although these are mainly CS in the femoral and trochanteral field, we see significant joint angle changes throughout the leg and not just in regional joints. And that is what's on my slide. All right, so in conclusion, campaniform scintilla locations are very robust. However, the relative arrangement within these locations differs between individuals, and the single campaniform scintilla locations on the leg have leg type specific locations. We saw that the field dynamics are influenced by the collars, sockets, and their material properties, and the sockets are interconnected in units and kind of function as a displaceable units that can affect cap displacement. And finally, the trochanteral and femoral field campaniform scintilla affect inter and intraleg coordination and may have multi-joint effects. So as a final kind of what am I doing now slide, since yesterday, I'm physically in the lab from Nick Shashinsky at the West Virginia University. And this is cool because they have robots here that have control systems that are modeled on the anatomy and function of the insect nervous system. So we are planning on basically taking this data from, especially from the morphology section of this presentation, and testing what effect does this variability of the sensor location actually have, which is something we can't really do in the physical fly. And then once we have these biomimetically correct sensors placed within, for example, a walking robot or an individual leg, we can actually do some tests that we can't do in the fly due to the limitations that the genetic tools provide. So we can, for example, see what happens or what is the relevant of the different sensor location of the single femoral CS. those are our plans, at least. Right, and with that, I would like to thank my funding agencies and all my collaborators. And thank you for your attention.
Thank you very much.
I have no idea with my time. I forgot to reset my timer, so.
You're perfect. You just ended on the exact minute. You're a
Oh,
minute.
really? Oh, nice.
Yes. Okay, so we have several minutes for questions for our presenter, and then we'll be switching over to the general discussion. So any questions? I have one quick question I just wanted to ask. The fact that you see variability is fascinating. What would you say? Do you think that that variability has functional consequences under some circumstances, and that makes some flies a little bit more able to handle things? Or do you think it's just, it really doesn't matter as long as you're in the same region, you're going to get more or less the same results, and therefore it can vary and it doesn't matter?
Well, I mean, that is like the introduction from my grant. No, I don't, it's hard to say. We also see, for example, like, I don't think that if one sensor in a field has, I don't know, a 15-degree shift in comparison to a different fly, that's going to make a big difference. I don't think that. But we did see quite a few flies that in every location that has 3 or more CS, we commonly saw 1 or 2 CS missing or more. And I think that in those cases, it's neglectable for the system, but in the cases where everywhere it has 3 or less and something's missing, I think that might have effect. I think there's like a minimum value that has to be set, and then it's okay. But yeah, I don't know. It's really hard to say. It's like we also saw a lot of variability in our split Dufour lines with the actual labeling, and it's hard for us to test the effect of the morphology in Drosophila using the animals that we have, because there's variability on so many different instances. And I mean, there's also like innate differences in the actual walking of every fly that we look at. They all have, just like when your colleague walks down the hallway and you know, oh, that's, you know, so-and-so, that's the same thing for Drosophila as well. So it's really hard to, like, you know, really find what the causation is of these differences. I don't know.
Yeah, no, this sounds very fascinating. I wonder if you can create behavioral contexts in which small differences make a difference, and therefore you could pull out the variability more clearly. But that's for future. Anyhow, I see other people have questions. So Matt.
Yeah, it's actually kind of a very similar question. So it might be, you have to do a similar handwriting, but you have your strain maps, right? Where you kind of said your simulations, you could say, here's the field of the CSs and here's how they would respond to different kinds of inputs. And so I'm just like wondering, can you actually use that as a bridge to explain some of the effects of your different, the different lines, expression lines you have? You know, there were some that you showed which had kind of overlapping, except for one extra field or something like that. Or getting to Halella's point of saying, if you have different animals which have different spatial distributions of the CSs, can you predict the different sensory information that's coming in, and then make a guess in terms of, if you knock that out, how would it affect the walking, to explain the full richness of your behavior? I mean, obviously way ambitious, but just curious if that's a direction that makes sense.
Yeah. I mean, if I would start a PhD again next week, I would do something like that, where I would just like, I would have my flies, I would either do intracellular or calcium imaging in the leg, or try to, while I move the leg in very specific, let's say I'll cut off the distal femur, I'll put it in a piezo or something like that and move it, you know, in 18 different directions, and basically measure cellular activity while I do that or something. And then do the same thing with an FEA and basically say, okay, at this point, this and this CS should be experiencing compression. What happens if I actually do it in the animal? Okay, I also see cellular activity. And then I can always say, okay, well, I'm going to take this leg now, image it, and see what the morphology was like. And maybe there are some differences, you know, like, I don't know, 8 of these CS of that location we're actually showing a signal. This one wasn't, oh, it's missing, or it's on a 35-degree slant or whatnot. That is something that I would do, but it's, of course, I mean, that's a lot of steps. But yeah, that's definitely been in the room before. Yeah, I don't want to do another PhD.
Yeah, understood. Thanks.
Nick, do you have a question?
Yeah, Kayla, great talk. as always. So I guess I maybe have a similar question, but now in the motor output direction. So you were using deep lab cut to track certain points as specific subpopulations of the CS were activated or deactivated. Is that a correct summary?
We used deep lab cut to track the tarsal tips, so we actually like knew where the legs were in space, so to say. Yeah.
Right. Okay.
Yeah.
Cool.
Okay.
Yeah. So you know, everything you showed makes perfect sense, and like in terms of the way you displayed it, like sure, sometimes it moves, sometimes it doesn't. Have you looked at what like direction the foot moved in as a function of which CS were stimulated?
No.
Okay. Yeah, I mean, I guess I'm just curious, you know, as someone whose group has done a fair amount of fruit fly kinematic reconstruction, I wonder if we could take your data, look at what the directional response of the foot is in response to specific directions of force, that it might give some insight into like what's being controlled, if that makes sense.
Mm-hmm.
Where I think you're totally right. It's not clear if there's co-contractions or activating an agonist or inhibiting an antagonist or whatever.
I mean, it's like the first data set that I showed with the inter and intraleg inhibition, that's where I was like inhibiting individual CS or parts of groups. And I think this inhibition, I mean, there's going to be some redundancy in the system that kind of cancels out the inhibition of these individual sensors. And we don't have the lines at this point in time where we can say, okay, I'm just going to do the complete femoral field, the complete trochanteral field. And I think if that point is ever reached where we have those driver lines, these kind of things could be really cool. At this point in time, I don't actually think that it's that relevant. I don't know. It's like, no, not your experiments are relevant, but like, I just don't, yeah. I don't know where I'm getting with my answer.
Tease out, for sure.
Yeah.
No, just spitballing. Thank you.
Bill, you have a question?
Yeah, I see a question from William Norse.
Yeah, that was a great talk, very interesting. My question comes for the variability from individual to individual as to like the arrangement and kind of locations of some of these CS. I guess my thought that I kind of wonder is, did you look at, you know, if there are any trends for how that variability corresponds to the physical variability between the individuals? You know, so if, you know, the different leg segments, length, mass or length are different from individual to individual, does that correspond to some of the changes from individual to individual about how the CS are arranged? You know, maybe it's accounting for the different kinds of, you know, stress it might be trying to measure as the animal's moving. Is it something that, you know, has it been looked at in any way?
It has not been looked at. To my understanding, it hasn't been looked at. It's a good idea for sure. I think personally that the reason why there's this like morphological difference in the sensors is actually the development of them. So basically, during the development of these external sensory structures, like a cluster of cells is there. One of them becomes a sensory precursor cell, inhibits all the rest from also becoming a sensory precursor cell. And then there are, when something happens to that precursor cell, a different cell comes up and is that new cell. So there's always going to be some, like, I don't know, whatever happens to that cell, and then the bottom right one beside it is going to become the next one. Or in the other case, it's going to be the bottom left one of this cluster that becomes it. I think that already creates a level of just randomness in this thing. Because it's also something that we see, let me find this slide. Nope, that's not it. Because the actual reason why it's so difficult to find CS labeling lines is because they're so closely related to the hairs, which is also part in this developmental thing where there's just one or two homeobox genes and their gradient depicts if it's going to become a bristle or a CS. And we actually see that, I don't know why I can't see it right now, right here. Right here, where this thing right here, that's actually kind of like a preliminary hair. In other individuals, it's ACS. And I think like on this level of kind of like developmental genetics is actually the causation of this variability. Of course, it could also be that some legs are longer, need a sensor more or whatnot. But if I would have to put $100 down on the table right now, I would think it's this. But it's for sure a good, at least master thesis project that somebody should do.
No, that makes sense. Thank you.
Well, this is a perfect time. We now have reached the end of all the formal presentations in the question and answer session, and now we have a half an hour in which people can have a freewheeling discussion of the various things that were raised during this workshop. Roger, I don't know if you want to start off by raising provocative questions or if you just want people to see if they have things that they would like to discuss.
I would actually like to start out with, okay, so we've seen talks with vertebrates and with insects, and very different. And we also had to talk about scaling. And the question is, okay, Matt started out with a. Actually, Nick asked Matt if there were like strain sensors in vertebrates, right? Wasn't that a question, Nick? So, are there other similarities? There's lots of differences. Obviously, I'm reaching here, asking about comparisons. Can we talk about some similarities, things that we see in these very different animals? I mean, just from the fruit fly, the stick insect, it's a hugely different scale, and we see on Greg's chart that we're expecting some differences there, based on length and time, and so anyway. This is a basic idea. Is Matt Trash? Are you still there? Okay. Let's start out by talking about the sensing. Force sensing, strain sensing. Did you see anything that like rings a bell from what you just heard from Gesa on this little tiny fruit fly? Anything that rings a bell in terms of what you see with vertebrates?
I stepped away for the beginning of your thing, so I kind of just catching up. You're just kind of looking for similarities across the animals in terms of sensation.
Yeah, right. And I'm throwing out in terms of force sensing because we heard a lot about strain sensing, for example, and in vertebrates we have various ways of doing force sensing. So I'm just wondering if there's something that can be said about similarities between those very different animals.
So I don't think I have anything profound to say, but I mean, clearly there are similar kind of modalities in general coming through. I think kind of a big difference, I think to maybe to some extent you could say with the vertebrates is especially like when you get to like length sensing is the efferent control. That's a difference. I'm sorry. So you wanted similarity. So sorry, but that definitely changes what the system can do in terms of controlling the information. I think there's also like and maybe this is my ignorance as well, but the sensors that Gesa was talking about are tied to the actual skeleton, as opposed to things that are within the actuators, and whether that gives a difference in terms of the information that's coming out, because there's not really the similar kind of to get the forces within, like kind of going to Nick, the forces within the skeleton in a vertebrate, you have to go through your muscles to get to that, to estimate that, and that's a distinction in that way. I don't know if that the nature of the fidelity or the how direct the information coming from the peripheral sensors into telling you things about the overall limb differs between those two. But that's me just kind of hand waving right now. But Ansgar probably has more direct things to say.
No, just what I wanted to ask you, Matt, exactly, because Corinna Geberhardt and me published a paper in Jane Wolf's last year because what Corinna found was unexpected, because you know, we have unmyelinated axons in insects, okay? And there is some of the specific sensors, I think the two sensors in vertebrates, which are non-myelinated, which are a bit slower. So, because what Corinna could show was, and that was for me quite unexpected, is that the difference in the conduction and the processing between the action potential generated in the sensory neuron at the place of origin, yeah, and the arrival at the motor neuron, even if you would say, oh, the ones which are further away from the central nervous system simply have a worse chance in invertebrates because there's non-myelinated, so they take longer. No, we found that specifically force sensors have a longer latency, which essentially is not covered by the distance. So the question is, how well is it known about the traveling time conductions? Because I didn't find anything, for example, 1A, 1B efferents or type 2. Can we consider this to be irrelevant because wherever the signal starts, being it here or here, it will be fast enough to affect the central networks in the same time frame?
So you're asking kind of, do latencies matter essentially?
Yeah.
I mean, I think you can see the differences in the latencies to some extent, right?
Okay.
Because you can see that, you know, the 1A reflex and things like that comes at different times in terms of the EMGs. Whether in terms of the mechanics that actually makes a significant difference, I would be less. I would think that the muscle, the force generation properties of the muscles and the mechanics of the limb would tend to filter out those differences, and it wouldn't make such a significant difference in that way. But it's not something I've looked at very closely to know. I mean, I think one of the things I think it's very striking though is, like, I mean, for joint efforts, you know, that like the conduction velocities there are so long. I mean, they're quite slow. I mean, it's and whether that would be able to play a role at the level of kind of the moment-to-moment control at the knee joint, you know, like that's not. I don't think that that latency and that speed might not be able to accommodate that. But I think what you're suggesting is that it might not, those analyses might not be that informative, and I should, you know, pay more attention to the kinds of things that the paper that you just described, essentially.
Thank you.
There is a question in the chat from Vidisha. Can the stick insect sense if there is a sudden change in height in their ongoing path and then stop walking? And if yes, how do they sense it? Ansgar, you might want to handle that. It's up to you.
Well, it depends. Where they definitely have height control in trying to find what one may call an optimal neuromechanical organized height, but which is operating differentially in a distributed fashion. So there's no central control of it; just comes along with the individual legs having a specific posture. What do you mean by height in the path? Yes, they actually do. Well, I would say the following: when, for example, when there is a small elevation coming or so, it's automatically fixed by the mechanical coupling through the body and the ongoing movement. I don't know that the insects do have an active height control system for sort of summing up and integrating across all legs or so. There is definitely an anti-gravity posture control system, which is known for 60 years now, but then my fantasy stops, or knowledge.
I just want to weigh in a little bit, if I could, about the scaling thing. One of the things that's very interesting and be worth thinking about, when you look at the scaling of axons, if they're unmyelinated, things scale with the square root of diameter. And so you really have to make things rather large in order to maintain the same conduction velocity. Whereas myelinated, it seems to scale with the diameter, which means that, you know, as things go on in length, you would have to do less increase in diameter in order to maintain the same scaling. I don't know whether that would have an important impact, but if we were dealing with control issues either for sensing or for motor stuff in very large animals, the scaling constraints on the axons might be very important for thinking about what delays would happen unless they were scaled, or could explain the kind of scaling of axons that you do see in these animals. So I just thought I'd mention that. Roger, you had something you wanted to say.
Oh, I was just going to bounce out what Ansgar said about height control or posture control and like stick insect, and I was just going to ask Matt, what are your thoughts in terms of like four-legged vertebrate beasts, in terms of height control or posture control? Is there rats have a particular cats, it's height controls really just pretty much straighten out their legs, right? But rats are more they have more of a they could change their height. They don't walk like a cat or like us with their knees straight. So the question is there what do we know about posture and height control and these kind of creatures?
I mean, I'm not sure that I know that much to be able to answer that in any authoritative way to say. I mean, I think there's I'm thinking it's mostly in terms of cat literature where people have talked about kind of strut length and strut angle control for controlling kind of like the posture of the limb and controlling height and controlling kind of forward after kind of that structure. People describe that in rats, but not as much. So I'm thinking of like the work of Lacquaniti and things who have kind of tried to describe that cats can control like the strut length and the strut angle independently of the individual joint angles and things along those lines. So that kind of the aggregate, treating it essentially as a virtual limb as opposed to the actual but where that's controlled centrally and how that's actually coordinated between limbs, I think I wouldn't have that much to be able to say for that.
Nick, I wanted to ask you, if you didn't mind contributing.
Sure.
Gaze has just started on this journey, but I think you've gotten some interesting preliminary results on the way in which the deployment of the sensors affects the ability of the system to respond effectively. Do you want to comment on any of that, and also the effective scale?
Yeah, I'll muse a little bit. We haven't done a whole lot looking at those specific kinds of issues and questions that Geza raised, which is why her arrival here is so exciting. Typically, we do add things like strain sensors to our robots, and they are directionally sensitive. And so that is something that clearly makes a quantitative impact on what feedback the nervous system can receive or does receive. I think, as Geza said, and as others have said, it's not clear if that's a behaviorally relevant difference. And so that's something that kind of remains to be seen. A couple interesting things that we've come across as we've worked on this problem is that, first of all, having multiple sensors and multiple arrangements certainly increases the richness of what you can measure, which I think is really exciting. I think in robotics, people are typically mounting 6-axis load cells to things, and they're just coming up with vectorial forces, and they don't really think about it any further than that. But if you're actually measuring the strain, you have effects like the Poisson effect, where if you stretch something and you elongate it, you also compress it in the transverse direction. And so what's cool is that in these strain sensors, we already see that, such that if the leg is loaded and it causes one axis to fire action potentials, when the leg is unloaded, it then recompresses, and that causes action potentials to be firing from the sensor in the orthogonal direction. And so one of the things I think I'm excited about exploring with Geza's work so much is that by looking a little bit more closely at the biology, you end up getting all this more information that you would not have had otherwise. And I think that that's a really exciting opportunity for robotics. And I think it's fun that we can model these kinds of things that people have been describing in the neurophysiology literature for decades now.
The other thing
Yeah,
I was
go
going
ahead.
to push a bit. I was just going to push a little bit on the scale issue, which Greg
Yeah,
briefly
right.
raised. But I think, what does that imply both for robotics and for animals for what needs to be measured?
Yeah, okay, sure. So yeah, so this is another question that's definitely worth thinking about. And I think it's complicated because it's not clear what parameters the animal is controlling in these different cases. So let me do my best to expound on that. So at least when I think of proprioceptive, when I think of movement feedback, right, I'm always thinking about things like position feedback, because that fits in with what Greg said about having some sense of what your equilibrium posture should be. And then also having some kind of velocity feedback to help damp out motions if they're too fast, to try to remove energy from the limb. I think some of what we've done suggests that as you get bigger, like Greg said, you need to much more actively consider removing energy, and that would show up in the form of negative velocity feedback. But what I think is interesting is that some of these small animals may be so damped. Oh, Ansgar, just about to shout you out. No, that in smaller animals we do see direct movement sensor to motor neuron connections, which appear to be positive velocity feedback, which is in effect some kind of anti-damping. And that has been tied to things like speed control in the locomotion of stick insects. Gabriel and Bushka's paper, I think, was, yeah, okay, just making sure I'm thinking of the right thing. Yep. So I don't know if there are effects that look exactly like that in vertebrates. That's just simply not my area of expertise. But yeah, I think it's very clear that at least mathematically there are new opportunities when you're small. You can undamp yourself with your muscles, which might help you move more quickly than your physics might allow. And honestly, I still feel like you'd want to measure load whether you were big or small. So I don't have anything to say in that specific area. I've been thinking about it, but I don't know if anything strikes me at the moment.
Thank you. That's really
I
very
don't know
helpful.
if that really addressed anything at all.
No, that's actually very helpful. Ansgar unfortunately has to go. I just want to thank him for having participated. It was wonderful. Be well and good luck on catching your train. Roger, do you have other things that you would like to raise and discuss?
Okay, so you just talked about feedback, negative feedback, positive feedback. So we saw from Greg that we expect positive feedback for these little animals, these little. Do you think they're really doing positive feedback, or do you think they're doing something that's akin to positive feedback? I'm asking Nick because Ansgar is gone.
Yeah, well, I mean, I'd also love to hear if Geza or anyone else has any thoughts on this. For a while, I thought that was a misinterpretation of the data. I think positive velocity feedback in this particular study that I cited, they very clearly show that action potentials from the velocity sensors are causing subsequent depolarizations in the motor neurons that would reinforce that motion. That's felt like as literal of a positive feedback loop as one could imagine.
And is that in swing or is that in stance?
This was in stance. Now it was an animal. I think it had 5 legs removed, and I think its thorax coxa joint had been glued in place. So it was a reduced preparation. But yeah, every time it would step on a treadmill, you would see the velocity from the pulling joint. You'd get spikes from the afferent there, and then you would see corresponding depolarizations in the motor neurons, and then you could see that the speed would increase as a function of whatever. So what I've been thinking about lately, that I'd love to hear anyone else's input on this. I think what seems more likely to me is that you might have task level positive feedback. So for example, if you're walking straight forward and someone pushes you from behind, that's just a free boost. Take that energy. Don't resist that with a negative feedback loop. Go with the flow. Now, if you're walking and someone pushes you to the side, you have to resist that. else you're going to fall over. Or if someone drops a 50-pound bag of rice in your arms, you have to resist that so you don't hit the ground. So once you transform positive body velocity feedback into the local control of all your joints, you might have some joints that look like they're doing positive feedback, and you might have other joints that look like they're doing negative feedback. But my engineer perspective is that that might all be completely irrelevant. Nah, not irrelevant. That's just a shadow of the whole picture, which is that the entire body is under particular vectorial control. So that's something we're working on right now. So nobody take that. No, I'm kidding. No, it's a huge question, and I think it's really interesting. But I like it also because it's the potentially, well, everybody's right kind of framework, or So I don't know what people think about that.
I think what you're pointing out is that when you have a distributed system that can in multiple ways respond to a perturbation, that assigning credit to any one part of it is problematic. And of course, one of the things we will tend to do by doing lesions and perturbations is to try to essentially immobilize everything else and get only that one thing to be the critical thing. But in many cases, you're absolutely right, it's shared among a whole variety of different things. And that's very important for the flexibility of the system. It actually also means, and this is very nice, that if you have some variability in the musculature, in the sensing, and so on, if it's a shared phenomena, then the fact that one thing is a little larger and the other is a little smaller doesn't really make any difference to you. It's interesting because, again, this I think is always very interesting in terms of the engineering. Since actuators are pretty expensive and sensors are it's hard for people to figure out how to integrate multiple sensors. They may not be that expensive, but it's hard to integrate. Often there's a tendency to skimp. And I think that's part of the reason that many of the artificial devices are less flexible, less robust, more brittle, because they basically one function, one input, one output. If any of that goes wrong, you're in terrible shape. Biological systems, you assume limbs can get damaged, there can be disease, all sorts of things can go on, but you want to keep on carrying on, so you distribute. So I think that there's probably a general principle there that may be worth exploring. So I definitely don't want to take it from you. I would encourage the other people, we could distribute the focus to other people to think about it as well.
No, certainly. And so, I mean, this is something else that Geza and I have talked a lot about in her first 24 hours here. So Geza, I don't want to steal your thunder, so feel free to jump in and interrupt. But
go ahead. My jet lag is still here,
okay.
So
yeah, that in the context of force sensing, Geza showed these kinds of patterns, and I've seen the full hour-long talk, and they appear to have different sensitivities and sort of different thresholds of activation. So the amplitude of the force is encoded more by a place code, which ones are active more than how active are they, or a little bit of both, let's say. But in any way, it's a very redundant system, because if one of these caps gets damaged, you have multiple caps that are deliberately measuring the same signal. They might have different dynamic ranges or different sensitivities. But and so this goes back into all the questions that Geza raised about redundancy and resiliency and even development, right? If you have some sort of developmental disorder, how do you make sure you can still walk? And so, I think this is a very important idea for robotics. If you actually want a machine that can survive for months or years or whatever, you've got to do stuff like that.
I also think this ties to Matt's work very, very nicely in terms of how you set up a motor system and the musculature in such a way that you minimize strain, but you don't do that necessarily based on one muscle's activation. It's the pattern of activation in the muscles, and you have it's not really redundancy, but you have some ability of them to substitute, overlap, interact in ways that keep the system doing what it's supposed to do. Matt, do you want to comment on that? Because that was one of the things I was struck by as I listened to your excellent talk.
I mean, just picking up on, the point, I guess, that Nick is raising, kind of the one extreme where you say, okay, you have the task, and you figure out the reflexes that are kind of necessary to achieve that task, and you just kind of rewire everything according to what you need to do. But we also know that there's some circuits that are going to be there within a limb that are maybe relatively preserved from one task to the next. And so like that tension, I think, is really, I still have a hard time getting my head around that. And how do we kind of define, are there reflexes or structures that we can kind of lay out that are good for that animal scale, period, and they are kind of common across tasks, but then you can layer on top of it the task specificity and the modulation. And other than taking kind of an evolutionary approach of kind of like, you want to take something that works for basic and then add on to the complexity, I'm not quite sure if there's a more principled way to kind of go after that question. I know that's not quite addressing what you were suggesting, Alel, but I was just kind of responding to what, like, Nick's point with that. And I don't know, I mean, because I don't, spinal reflexes do not get reprogrammed from scratch every time you change a task. There are changes, it's certainly modifiable, but it's not like you kind of like say, it's tabula rasa and you start out with something new, right? And so that tension, I think, is always, tricky, like how to lay that out in a principled way. So I'm still having a hard time thinking that through, but it's a really interesting one, definitely.
I see Geza has something she'd like to say, so let's hear from Geza.
I don't know if this is a super fitting comment for this discussion right now, but a recent paper from Phelps et al., I think it was 2021, basically tracked the projection patterns from various sensory structures in the leg of Drosophila into the VNC and characterized all the leg CS into 3 categories basing on their projection patterns. And only 2 CS from the leg basically project contralaterally and directly synapse onto motor neurons, and they're in the trochanteral field. And the other CS basically either project up and down, so like if they come from the meso, they also go pro and meta on the ipsilateral side. And the third category is basically staying local within that one ganglion. And I definitely think like these kind of findings with the morphology kind of going that direction, where we can see direct connections from some CS onto motor neurons and also some that go contralaterally and so on. I think we're gonna see quite soon that some CS are more important than others, not only because it's the location where they're at, but also within that location. Some preliminary things that I also looked at, like within one field, is that some have like some positive synaptic markers and stuff like that. And I think that we're simplifying too much, saying, okay, well, this group has 12 sensors or 11 sensors, it's going to be doing some range fractionation, blah, blah, blah. But actually, I think it's even more complicated than we want it to be, because they are very different, not only in size and orientation, but also in their connections, their transmitters, and so on. I kind of lost my path here, but yeah, so I think, yeah.
No, I think that's
yes.
I think that's consistent with what Matt's saying, though, right? That there's a multifunctionality built in, even at the, what I want to say, even sensors have specific roles, and you're not going to be messing with those, right?
Yeah.
Because go ahead.
That's also what I meant. Like in this, I got my final sentence back. It's kind of like that the redundancy is there, but only for some CS within one location. And we kind of have to figure out which ones are ignorable and
well, it's interesting because it may not even be redundancy. What it may be is that there are these overlapping functions. Again, this would actually go back to something that Matthew was referring to in his talk, which is that there are multiple ways of solving the problem, and the system may use many of them simultaneously. And then only under disease or pathological conditions do some of them get eliminated. And we see that there's, you can actually continue to function without them. So one of the drawbacks of our lesion approach, which is one of the only ways we have to manipulate the system, is that we can show our hypotheses are correct, but we haven't necessarily excluded that under ordinary circumstances is actually a set of several different overlapping things doing what needs to be done. And then as the functions change and the system has to be exercised in different ways, the relative weighting of those different things in that function changes, which gives it that richness.
Yeah,
I think again, if someone wants to make one or more comments, I think we're actually reaching the end of our time. But if people want to stay a little bit and have a few more comments, I'm certainly open to that. Yes, Ben, I think you want to say something?
Well, there's Alex here. This is my lab. I'm on Ben's computer.
Alex, then.
But yeah, I would say something that's really struck me is how useful sensory information is and how not necessary pretty much any single sensory signal is for a function, right? And so, yeah, there's just this large kind of capabilities of using different sensory signals to help achieve a particular task. And I think it's really kind of interesting that we can basically delete any signal and still get functional behavior out of an animal. And yeah, it has to do with this redundancy overlap. And I just wonder, if we can kind of dig in based on our kind of scaling stuff, if we can dig into what signals might be more critical for specific tasks. And other signals might be more periphery, but still helpful type of stuff. And then something else that I wanted to touch on, I guess with Matt, maybe we can take this offline at another time, was that I believe 10, 20 years ago, there was definitely this idea that there was positive force feedback in mammalian locomotion. And I don't know if that's still around or if it's morphed into something else, because Greg's predicting that it's not there. And yeah.
Well, he's predicting it'll be destabilizing in certain contexts. Matt.
Yeah, so I mean, this is, I think Richard Nichols is looking at that kind of force feedback pathways during locomotion and stance, and he finds predominantly they're negative feedback, and that they tend to stay the same from posture to locomotion. That is, as you say, there was a literature to suggest that there was positive, that it switched sign when animals are in behavior and there would become positive force feedback. He does find there is positive force feedback between, I think it's between some of the ankle extensors, but it's a very small subset of them, and that's there, but it stays the same across behaviors. So there is some, but it's not like it's a global force feedback. And then why it should be between those ones in particular as opposed to other ones, I think is still a little bit of a question. I think Richard has some really interesting discussions about it, but I think that's there. You know, it was a confusing literature for that reason, because essentially, like you say, there was that narrative, and I think when he looked at it more closely, it didn't seem to be there in the same way.
So I want to thank everyone for participating, and I'm going to give Roger a moment to also say a few words, but this has been a wonderful workshop, very exciting. I've learned a lot. I hope the members here, not just the speakers, but everybody who came in and listened. Again, I'm very grateful for your participation. I do want to remind people that the Living Machine starts tomorrow. I believe it starts at 12:45 Universal Time, which in the Eastern Daylight Savings Time is 8:45 a.m. So I think that some people may have been confused. I don't know whether we want, Roger, we want to send out a note to people to remind them to check their local times. But that certainly was one of the reasons why our first speaker ended up switching with our, the person who was our second speaker. And again, thank you, Matt, for stepping in at a critical juncture. But I think this has been really very exciting, and thank you all. Roger, I'll leave you for the last words.
Ken Moses has really tried to fight the battle of the time, the time battle, the time wars. So yeah, one of my students he said he also missed the talk because he was thinking 6 hours is European time instead of universal time, and it was anyway. Yes, I want to thank everyone. I want to thank the speakers, thank everyone for showing up, and hopefully we will soldier on tomorrow with our with a conference starting at 12:45 Universal Time, and
which Eastern Daylight Time is 8:45. If that helps.
You can just put it into Google what that means in your local time. That's my recommendation, because it just gets confusing for us to try to give everyone their time based on universal time. So that's why we stuck with UTC. So anyway, yeah, thank you very much for all the speakers. It was very enjoyable for me.
All right, everyone, I look forward to seeing you tomorrow. Thank you. And again, if this sparks other conversations offline, that's part of what the point of these workshops is. And I look forward to those conversations happening among members of the workshop and others. So take care, everyone.
Ken just pointed out there's a different Zoom site, different Zoom location for tomorrow.
Right. Yes.
So that's the other thing that might go wrong.
Right. So make sure to use the correct Zoom location. Well, all right. Take care, everyone. Bye-bye. Bye.